How vast is the universe? Does it have boundaries? These two questions have puzzled astronomers for thousands of years. Today, we know that the solar system spans about 2 light-years in diameter. With current technology, it would take tens of thousands of years to travel beyond it. Yet in the grand scale of the universe, the solar system is just a tiny speck, because the Milky Way alone contains over 400 billion star systems with similar structures. Even more astonishingly, within the observable universe, there are around 2 trillion galaxies like the Milky Way. In the past, astronomers believed that no structure in the universe could exceed 200 million light-years in diameter. Beyond this threshold, gravitational forces would be too weak to hold distant celestial bodies together, especially since gravity propagates at the speed of light. For a long time, the local supercluster, also known as the Laniakea supercluster, was thought to mark the limit of our understanding of large-scale cosmic structures. However, astronomers later discovered that the local supercluster, along with several nearby galaxy clusters, are collectively moving in the same direction. This loosely connected but coherently moving structure was named Laniakea, estimated to span about 500 million light-years. Although it's smaller than the Sloan Great Wall, a structure stretching 1.5 billion light-years, Laniakea still surpassed the previously assumed 200 million light-year size limit. At this point, an important question arises. Why are all these gigantic cosmic structures, so-called cosmic walls, or voids, located so far from us? Could it be that we ourselves are part of something even bigger? In 2013, astronomers boldly proposed that the Milky Way, and even the entire Laniakea supercluster, might be situated inside a cosmic void, a region of space with extremely low matter density. This void was named the KBC void, also known as the local void. It is estimated to be at least 2 billion light-years across, larger even than the Eridanus supervoid, a cold region with a diameter of 1.8 billion light-years discovered through cosmic microwave background radiation maps. Further studies revealed even more surprising insights. Not only are we inside a vast cosmic void, but our position is only a few 100 million light-years from its center. This explains why astronomers once believed there were no structures larger than the Laniakea supercluster, because we're essentially at the heart of a cosmic emptiness, with few surrounding galaxies to observe. This idea also closely ties into one of astronomy's most famous questions: the Fermi paradox. Why haven't we found any signs of extraterrestrial life? Some astronomers speculate that the outskirts of the Milky Way, where the solar system resides, and the encompassing local void might actually be a quarantine zone created by advanced alien civilizations. The purpose of such a quarantine would be to isolate technologically primitive civilizations, like ours. Only when humanity develops the technology for faster-than-light travel might we be able to leave this region and join the larger cosmic community, a realm teeming with intelligent and thriving civilizations. Like other hypotheses related to the Fermi paradox, we currently lack the means to test this bold idea. Perhaps in the end, humanity is indeed the only intelligent life form in the universe, and all our efforts to search for extraterrestrial signals are just a one-sided delusion. However, to be honest, this possibility seems unlikely. Earth-like planets and sun-like star systems are not rare in the universe. Even if the odds of alien civilizations existing were only 1 in 10,000, the total number of intelligent species across the cosmos could still outnumber Earth's population. As for the universe beyond the observable universe, the portion we can't see, astronomers believe there are still vast networks made up of countless galaxies. But due to the enormous distances and the universe's accelerated expansion, the light from those galaxies will never reach Earth. Therefore, we will never be able to observe them. If Einstein's theory is correct, then even if we travel at the speed of light in any direction, we'll eventually circle back to our starting point. That's because the mass of celestial bodies bends space-time, turning the measuring tape of the universe into a closed loop, much like a journey around the Earth. Thus, any voyage through the cosmos may end up looping back. In about 1 million years, another star will enter the solar system. Will we be able to witness two suns in the sky? The Milky Way, approximately 180,000 light-years wide, contains hundreds of billions of stars. Among them, the orbits of a few occasionally cross paths with the solar system. One prominent example is Gliese 710, currently about 63 light-years away. It is predicted that in roughly 1.35 million years, Gliese 710 will enter the Oort cloud, the outermost icy region of the solar system. Although it won't collide directly with the Sun, its gravitational force could disrupt the entire solar system's stability. Current simulations suggest that at its closest approach, Gliese 710 will be only about 0.19 light-years from the Sun. While this seems close, it's still much farther than Neptune, the outermost planet in our system. Therefore, astronomers are not particularly worried about a direct impact with Earth. In fact, the celestial bodies most affected by Gliese 710's intrusion won't be Earth, but the billions of comets in the Oort cloud and millions of asteroids between Mars and Jupiter. Among these, it's possible that large asteroids, similar to the one believed to have caused the extinction of the dinosaurs 65 million years ago, might be sent hurtling toward Earth. Currently, the brightest object in the night sky is Sirius, with an apparent magnitude of -1.4. But in 1.35 million years, Gliese 710 is expected to shine with a magnitude of -2.67, brighter than Sirius today. With such brilliance, Gliese 710 could illuminate the entire Oort cloud, causing many comets to glow and create a dazzling spectacle in the night sky. From Earth, observers might see an extraordinarily bright star surrounded by twinkling comets, an unprecedented celestial event. Throughout Earth's history, comets and asteroids have played a crucial role in the evolution of life. First, comets likely delivered vast amounts of water to our planet. Moreover, asteroids may have carried organic compounds or life-building elements, and upon crashing into Earth's early oceans, they could have sparked the beginnings of life. Remember, Earth formed 4.5 billion years ago, but single-celled life didn't emerge until about 3.8 billion years ago. This 700 million year gap might have been a period of intense celestial bombardment, seeding the planet with life. Only after Earth's orbit cleared of hazardous asteroids did it enter a stable phase conducive to long-term evolution. The asteroid that caused the dinosaur extinction 65 million years ago was about 10 kilometers in diameter, a very rare event. If no similar catastrophe occurs in the next few hundred years, humanity could realize its plans to settle on the Moon and Mars, officially becoming a multi-planetary civilization. In that case, even a 30-kilometer-wide asteroid wouldn't threaten us the way it once would have. However, compared to asteroids and comets, what truly terrifies astronomers are supernova explosions and rogue black holes. A supernova, the explosive death of a star, has triggered several smaller extinction events throughout Earth's history, with radioactive traces still found in geological layers. As for rogue black holes, although never observed up close, if one were to approach the solar system, human civilization would face utter annihilation. Unlike ordinary stars, a black hole can be tens or even hundreds of times more massive than the Sun. It wouldn't need to strike the solar system directly. Just passing nearby would wreak gravitational havoc. Its immense pull could fling Earth out of orbit, turning our world into a wandering Earth, a planet without a sun and devoid of life as we know it. Currently, the solar system is orbiting the center of the Milky Way at a speed of 120 kilometers per second, taking about 220 million years to complete one revolution. Over this immense time span, all celestial bodies around us are constantly changing, from the nearest stars to the closest black holes, all continuously updating. If there are a few black holes hidden behind nearby cosmic dust clouds, then as soon as their gravitational influence reaches the solar system at the speed of light, everything could be thrown into chaos, from Earth to the entire supercluster of galaxies. What does the universe look like from God's perspective? When viewed on a scale of tens of billions of light years, the universe resembles a massive web. First, stars gather into galaxies. Galaxies then group into galaxy clusters. These clusters combine to form superclusters. Superclusters, which can span tens of millions of light years in diameter, in turn come together to form even larger structures. However, we must remember that what we see is just an image of how it looked 12 billion years ago. By now, it may have been torn apart into smaller pieces by the relentless expansion of the universe. In an ever-expanding universe, with its acceleration possibly exceeding the speed of light, scientists find it difficult to conceive of the existence of an ultra-advanced alien civilization. That's because, under the speed of light limit, no civilization could effectively control regions of space beyond a few dozen light-years. As of now, the Kepler telescope has discovered more than 5,000 exoplanets, all within a range of 3,000 light-years from Earth. Meanwhile, the Milky Way spans 180,000 light-years and contains hundreds of billions of stars. Thus, astronomers tend to believe that intelligent civilizations, varying widely in technological levels, are scattered throughout our galaxy, Earth's civilization being just one among many. These civilizations might be thousands of light-years apart. Hence, discovering one another is already difficult. Establishing communication is even harder. Moreover, we often assume that life requires water and oxygen. But in reality, entirely different forms of life may exist, such as silicon-based life, which doesn't require oxygen or water, and might even be better suited for space exploration than humans. Does silicon-based life really exist? Until now, astronomers have based their search for extraterrestrial life on Earth's biological standards. There's an almost universal assumption that life cannot exist without water and oxygen, a perspective clearly flawed. After all, early life on Earth was anaerobic. Only after the Great Oxygenation Event, when oxygen flooded the atmosphere, did 99% of anaerobic organisms go extinct. Those that relied on oxygen then continued to evolve to this day. More importantly, life on Earth is based on carbon. But in the periodic table, there are other elements capable of forming life-supporting structures, depending on environmental conditions. A promising candidate is silicon-based life, which requires neither water nor oxygen and thrives in high-temperature, high-pressure, and radiation-filled environment. To humans, they might appear to be just lifeless rocks or crystalline clumps, but the unique properties of silicon could allow them to think faster and possess superior intelligence. From a space exploration perspective, the near-absolute cold and harsh radiation in outer space pose no threat to silicon-based life. They could freely exist on many planets across the universe. In fact, when they arrive on planets like Earth, the presence of water and oxygen could cause them to rust or short-circuit, triggering destructive reactions. That's why planets deemed uninhabitable for humans, like Venus, might be ideal environments for silicon-based life. Looking further ahead, if humans want to shed bulky survival equipment to move freely in space or on alien planets, we will need to modify our own bodies. For example, implanting mechanical components to adapt to harsh environments, or even replacing the entire body, keeping only the brain, to survive without water or oxygen. Many scientists believe that silicon-based life will be the dominant force in the exploration of the universe. In fact, the processors and artificial intelligence, AI technologies being developed today are, in some sense, a form of artificial silicon-based life. If in the future AI truly replaces humans as Earth's dominant species, it will continue to evolve, expand into space, and explore the cosmos on our behalf. What's notable is that very few people recognize this today. Perhaps, only in the end, will humans realize our existence might have simply served to develop chips and artificial intelligence, laying the foundation for the birth of silicon life, and ultimately, humanity will be replaced. In current science fiction, the clearest representation of silicon-based life is the Cybertronians in the Transformers series, beings entirely composed of metal. Their transforming ability appears when they come to Earth, but on their home planet, their bodies also have a symmetric structure with heads, torsos, and limbs, similar to humans. Of course, this is still fiction, so it's understandable that they resemble humans. But what would real silicon-based life look like in the universe? We can only be certain that these life forms would have a metallic or stone-like structure, and Earth-based biology would have no effect on them. From mastering controlled nuclear fusion to building Dyson sphere-scale structures, humanity could gradually transition from a Type 0.7 civilization, our current level, to a Type 1 and even beyond to Type 2. However, reaching Type 1 will still take at least 300 to 500 more years, and Type 2 might take tens of thousands. Concepts like light-speed spacecraft or wormhole technology remain within the realm of science fiction. Instead, practical scientists are focusing on developing fusion-powered spacecraft combined with hibernation technology. With such designs, even if the spacecraft only reaches 10% of light speed, it could still reach nearby star systems within a few hundred years, a fully feasible timescale for future interplanetary colonization missions. But even if humans can leave Earth and expand into space, the Milky Way remains an enormous realm, nearly impossible to fully explore. The solar system is just a tiny component within the Orion Arm, a minor spur on the galaxy's outskirts. Around the Sun are only a few dozen nearby stars, while the entire Milky Way contains hundreds of billions. Therefore, even if humanity reaches its peak, we may still remain a small, solitary civilization in a cold corner of the universe. Earth is slowing down. Will it eventually stop rotating? Over the past 650 million years, the length of a day on Earth has increased by about 2 hours. Due to the law of conservation of angular momentum, the distance between Earth and the Moon is also gradually increasing, currently reaching approximately 384,000 kilometers. In the future, the influence of tidal forces, caused by the gravitational pull of the Moon and the Sun, as well as human space activities, will continue to slow down Earth's rotation. However, with the current deceleration rate of only about 1.8 milliseconds per 100 years, Earth will not completely stop rotating before the Sun turns into a red giant and engulfs our planet, about 5 billion years from now. In reality, Earth will never stop spinning on its own, unless we intentionally force it to, like in the sci-fi film The Wandering Earth, where humans build massive planetary engines in the opposite direction of Earth's rotation to halt it through sheer propulsion. For this reason, astronomers continue to use Earth-based standards when searching for extraterrestrial life, because at the very least, looking for carbon-based life allows us to apply known biological evolution rules. However, beyond carbon and silicon life, some scientists believe that the universe may contain gaseous life forms, or even plasma-based life. These beings might live in the atmospheres of gas giants or on the surfaces of stars, where conditions are extremely harsh. They could form from the combination of countless simple structures, creating complex life forms that span tens of thousands of kilometers. Can humans reproduce in space? Although Earth, the planet beneath our feet, will remain humanity's only home for a long time to come, the ongoing development of near-Earth space and future exploration of the solar system will lead many to live in space, where microgravity and vastly different survival conditions exist. In that context, human reproduction in space is no longer just a scientific issue. It's a matter of survival for our future civilization. If humans can't reproduce in microgravity, we won't be able to settle permanently in space, and the dream of cosmic exploration will come to a halt. In 2023, Japanese scientists conducted an experiment on the International Space Station, ISS, using fertilized mouse embryos, successfully growing them into blastocysts, the early stage of embryos with cell division. Compared to a control group on Earth, the development rate of blastocysts in microgravity showed little difference, and even tended to produce more identical twins. Although no direct experiments have been conducted on humans aboard the ISS, the results from mice, whose genome is very similar to humans, strongly suggest that mammals can develop embryos in microgravity. This indicates that biologically, humans also have the potential to reproduce in space if the technical conditions are right. In reality, the greater challenge is technical, not biological. First is the problem of microgravity on current space stations. In the future, we could build rotating cylindrical stations that use centrifugal force to simulate Earth-like gravity, reducing the harmful effects of weightlessness and preserving natural daily routines. Next is the issue of cosmic radiation, a serious threat to fetal development. However, current space stations already have special radiation-shielded compartments, and future large-scale space cities will certainly be designed with this in mind. Compared to animals, plant cultivation and breeding in space have already made significant progress. So as long as large enough space cities are built, creating a closed ecosystem where humans can live, work, and reproduce in space is entirely achievable. Humans could definitely achieve self-sufficient agriculture in space. Currently, the veggie planting system on the ISS has been used to grow various crops, including kale, peanuts, and wheat, providing fresh food to astronauts in a closed environment. However, for humanity in the future when living long-term off Earth, the greatest concern remains cosmic radiation. Galactic rays and high-energy particles from the sun can damage DNA, causing genetic mutations. Under constant radiation exposure, reproductive cells may also suffer mutations. And if passed down, these could lead to birth defects or serious hereditary conditions. Suppose a child could be born healthy and grow up normally in microgravity. Their body, both in physiology and bone density, might still be unable to adapt to Earth's 1G gravity. This would mean that such children would become true space humans, no longer suitable to live on their home planet. In summary, the task of living and maintaining human reproduction beyond Earth is an inevitable challenge that humanity must face. Currently, experiments with plants and animals have not revealed any insurmountable biological obstacles. Although there are many unfavorable factors in microgravity affecting life development, these barriers can be overcome with technology. Thus, the future expansion of human civilization into space will proceed with strong support from advanced technologies. As the father of space travel, Konstantin Tsiolkovsky once said, "Earth is the cradle of humanity, but mankind cannot stay in the cradle forever." Why do astronomers believe that? Even if we reach the speed of light, we still can't touch the edge of the universe. You'll understand this by looking at the facts. Voyager 1, the spacecraft launched in 1977, is currently about 24.5 billion kilometers from Earth, traveling at a speed of 17 kilometers per second. And yet, it would still take another 30,000 years just to exit the solar system, which has a radius of only 1 light year. Even if we could build a spacecraft that travels at the speed of light, it would still take 1 full year just to leave the solar system, slower than modern flights around the Earth. What's more concerning is the increasing delay in communication. A spacecraft traveling at light speed would be unable to receive real-time responses from Earth. And Earth couldn't transmit real-time commands back either. This delay would make remote operations virtually impossible on long-term missions. Suppose we aimed to reach Proxima b, a potentially habitable exoplanet. Even traveling near light speed, the journey would still take many years. If we continued flying perpendicular to the plane of the Milky Way, it would take about 3,000 years to exit the galaxy. 2.54 million years later, we'd finally reach the Andromeda Galaxy. And if we had the time and technology to continue flying, it would take about 93 billion years to cross the entire observable universe, even at the speed of light. From those numbers, it's easy to see. The speed of light, on the scale of the universe, is not much faster than a crawling turtle. Controlling a light-speed ship to explore the universe is no different than an ant trying to walk around the Earth, painfully slow and impossible within a human lifespan. And more importantly, that's still not the biggest problem. This is why the only technology that might allow humans to reach the edge of the universe in the future is the wormhole, a shortcut through space that bypasses the speed of light limit. However, if the universe truly is a four-dimensional hypersphere, then even if we reach its edge, taking just one step forward might bring us back to where we started, on the opposite side. Just like traveling around the Earth, go far enough and you'll return to your starting point. Therefore, to escape this looped enclosure, humanity would need to break into a higher dimension. Currently, the universe we observe and interact with has 3 spatial dimensions: What we often call the fourth dimension is in fact just time, not an actual spatial dimension. Perhaps in the future, humanity will discover a new theory of space-time that surpasses general relativity. Only then will scientists be able to truly open the door to higher dimensions, allowing us to approach the edge of the universe, or even escape it entirely. This is much like how humans were once bound to Earth by gravity, until we invented rockets and flew into space. What once seemed like an absolute barrier was eventually overcome through technological breakthroughs. So, if we return to the original question whether the speed of light is the ultimate limit of the universe, it's now clear that the speed of light is not a universal master key. Even if we could reach it, humans still wouldn't be truly free in the cosmos. Some scientists even believe that the speed of light limit is just a partially closed door, effective only within our observable region. Beyond that region, the speed at which light travels in a vacuum might be far faster. But all of this remains unverified theory, because as of now, we lack the technology to confirm it. The night sky after 3.75 billion years. When the Andromeda Galaxy comes into view, will that be the doomsday for the Milky Way? As the two largest galaxies in the local group, the relationship between the Milky Way and Andromeda has always fascinated astronomers. Over a century ago, astronomer Edwin Hubble discovered the blue shift of Andromeda, indicating that this galaxy is moving closer to us. Modern calculations, based on the relative velocity between the two galaxies, suggest that a collision will occur in about 3.75 billion years. During that time, Andromeda will gradually dominate the night sky, covering more and more of the observable area, until it spans nearly the entire celestial dome, creating a once-in-a-lifetime spectacle. The two galaxies will not collide in the traditional sense, as the distances between stars are vast, but they will merge into a massive new galaxy, possibly named Milkomeda or Milkdromeda. This will be one of the greatest astronomical events in the nearby universe, marking a turning point not only in cosmic structure, but also in humanity's long-term survival journey. However, a recent study from Durham University has introduced a new perspective. The probability of a collision between the Milky Way and Andromeda within the next 10 billion years may actually be less than 50%. The reason is that previous studies only considered the motion of the two galaxies alone, ignoring gravitational disturbances from other members of the local group. Specifically, although the other galaxies in the group are small with weak gravitational forces, over tens of billions of years, the cumulative impact of these small forces may significantly alter the orbits of the two main galaxies. Based on data from the Gaia satellite, astronomers have found that within a 10 billion year time frame, Andromeda is more likely to pass by the Milky Way rather than collide directly. In fact, the chance of a collision in the next 5 billion years is only about 50-50, not a certainty as once believed. However, if we take dark matter into account, the situation might change. The distance between the Milky Way and Andromeda is currently only about 2.5 million light-years, and both are massive galaxies with diameters over 100,000 light-years. Therefore, the dark matter halos surrounding these galaxies may extend hundreds of thousands of light-years. As a result, interaction and merging within these halos may begin long before the galactic cores actually meet. Future astronomical threats. Not just galactic collisions, but changes in the Sun itself. Aside from a potential collision with Andromeda, a more immediate threat to life on Earth comes from the Sun itself. According to calculations, the Sun's brightness increases by about 1% every 100 million years. If this continues, in just 1 billion years, the Sun will be bright enough to evaporate all oceans on Earth. At that point, the habitable zone around the Sun will shift outward, to the orbits of Mars or even the moons of Jupiter. This shows that the habitable zone in the solar system has never been fixed. In the past, Venus may have been a habitable planet, and ancient Mars once had an atmosphere and oceans. Earth simply happens to be in the survival window right now. Therefore, in order to continue existing, humanity will inevitably have to expand beyond its home planet. The first steps involve establishing bases on the Moon and Mars, followed by exploration of other celestial bodies within the solar system. Although no planet in the universe is completely motionless, many planets do exist that permanently show only one face to their parent star. For example, Proxima, located 4.22 light-years from Earth, or Gliese 581g, about 20 light-years away. Due to their close proximity to their stars, these planets experience tidal locking, meaning they always present one side to their star, just like the Moon always shows only one face to Earth. Among the more than 5,400 exoplanets we have discovered, many are tidally locked because they orbit too closely to their host stars. These planets only have narrow twilight zones, between the scorching day side and the frozen night side, where conditions might be suitable for life. Planets like Earth, situated in the habitable zone, not too close to the central star, and equipped with a protective magnetic field, are truly rare in the universe. This is why most astronomers believe that life and civilization are extraordinarily rare. It may also explain why we have yet to find signs of extraterrestrial civilization. Looking back at Earth's formation, since its birth 4.5 billion years ago, it took until 3.8 billion years ago for the first signs of life, unicellular organisms, to appear, discovered in deep-sea hydrothermal vents. This means it took Earth about 700 million years to go from nothing to life. Even if we subtract the first 200 million years for the planet to cool, life still needed 500 million years to emerge. This extended period poses a major challenge for many star systems in the universe. Red dwarfs are too small and emit intense radiation, while larger stars have very short lifespans, often burning out in less than 500 million years. Only medium-sized stars like our Sun, yellow dwarfs, have stable life cycles lasting billions of years, giving life enough time to emerge and evolve. Moreover, the solar system's location in the Milky Way is also ideal. It's not at the galactic center, where supermassive black holes and violent astronomical activity occur, nor at the fringes, where it's easier to be ejected into intergalactic space. The solar system, like its third planet, occupies a stable middle ground, neither too close nor too far, perfect for sustaining life. Therefore, a life-supporting planet is the result of many overlapping habitable zones. First is the planet's position within its star system. Second is the star system's position within the galaxy. Only when both are stable can the fragile early stages of life be protected from sudden astronomical upheavals. Overall, even though we know that the Earth is slowing down or doubt the existence of extraterrestrial civilizations, all of these matters are still far off in the future. Meanwhile, the most urgent mission for humanity in the near term is to explore nearby space, starting with the Moon, Mars, and near-Earth orbit. Only when millions of people are working and living in space can we truly reach Type 1 civilization, capable of fully harnessing the energy of our home planet. From there, we can continue expanding across the solar system, the Milky Way, and further into the distant universe. It is only through this process of expansion and exploration that we may truly have a chance to find life beyond Earth. Astronomers discover a super-Earth with a year lasting only 32 days. Could life exist there? Currently, scientists refer to planets that are larger than Earth but smaller than Neptune and composed primarily of rock and metal as super-Earths. Among the more than 5,000 exoplanets discovered so far, over 30% are super-Earths, meaning more than 1,500 planets. However, only a very small portion of these lie within the habitable zone, regions where atmospheres and oceans might exist and conditions may support life. The most promising candidate for sustaining life, and also the one closest to Earth, is Gliese 581, a planet located around 20 light-years away, with a mass about 4 times that of Earth. Its host star is a red dwarf, much smaller than the Sun, comparable to Proxima Centauri, the closest star to Earth. As a result, Gliese 581g is very close to its host star and has an extremely short orbital cycle, 1 year lasts only 32 Earth days. When it was first discovered in 2010, many astronomers were optimistic about the possibility of life there. The reason, the habitable zone around a red dwarf is very narrow, and Gliese 581g lies precisely within it. Moreover, red dwarfs emit relatively low energy, so instead of evaporating oceans, they might only slightly increase radiation, still within survivable limits for deep-sea life forms. However, the biggest issue is, Gliese 581g is very likely tidally locked to its host star, meaning one side always faces the star, while the other remains in permanent darkness. Under such conditions, the only potentially habitable region would be a narrow strip along the boundary between night and day, where dim light and stable temperatures might allow life to exist. Life, if present, could evolve and thrive in that perpetual twilight. To date, we have not detected any signals from Gliese 581g. At a distance of 20 light-years, if an advanced civilization existed, their electromagnetic waves should have reached Earth by now. Moreover, the planet's atmosphere has shown no abnormal rise in CO2 or industrial compounds, indicating that if life exists, it is likely still in its early stages, possibly at a Stone Age or primitive agricultural level. At a distance of 20 light-years, could Gliese 581g become a new home for humanity? In reality, 20 light-years is not too far in the context of humanity's future. Although light-speed spacecraft and wormhole technology are still science fiction today, within the next few decades or centuries, we may successfully develop nuclear fusion-powered spacecraft combined with hibernation technology for the crew. When that time comes, planets within several dozen light-years, like Gliese 581g, 20 light-years, or Proxima b, 4 light-years, will become viable targets for exploration and long-term colonization. These planets could serve as new bases, or even a second home for human civilization, marking the beginning of an era of interstellar expansion. Beyond serving interstellar travel, human hibernation technology may also hold another potential: time travel. A long sleep could allow people to pass through decades, awakening in the future. However, this would only be desirable if the future were better than the present. If the future is uncertain, chaotic, or even terrifying, very few would willingly choose to sleep for years, only to wake up in a strange world, alone, without loved ones or familiar faces. All in all, 20 light-years is not a great distance on the cosmic scale, and with some effort, the future of human civilization may reach it within a single lifetime. Thus, the practical expansion range for humanity may focus on a sphere within 50 light-years of the solar system, a region still accessible using hibernation and fusion propulsion. As for stars farther away in the Milky Way, unless we can construct a network of interstellar wormholes, humans will not be able to reach or explore them. Even though hibernation is useful, it still has time limits. Lasting for several decades is already a major challenge for human physiology and psychology. Perhaps in the future, humans will evolve into a half-biological, half-mechanical species, better suited for surviving harsh space environments, becoming the dominant race of the cosmos. Or perhaps, another possibility, human consciousness will be uploaded into computer systems, living in a virtual world free from disease, physical constraints, and forever in a state of peace and freedom. There is something scarier than a black hole, white holes never seen before. Could they lead us to another universe? In 1916, Albert Einstein published his theory of general relativity, in which he predicted the existence of three extraordinary space-time phenomena: black holes, wormholes, and white holes. To this day, astronomers have confirmed the existence of billions of black holes in the universe and have even captured direct images of some supermassive ones. However, for a wormhole to form, it requires an extremely unstable space-time structure, something our current universe doesn't seem to support. As such, scientists believe wormholes, if they exist, do not occur naturally. Among Einstein's three predictions, the white hole remains the final, unfinished piece, the missing component of general relativity. In theory, a white hole is the mirror image of a black hole. While black holes absorb everything and never release it, white holes constantly eject matter outward, without end. Suppose higher dimensions exist, then matter swallowed by a black hole in this universe could be released from a white hole in another universe. The problem is, our universe contains hundreds of billions of black holes, all endlessly eating. If this matter must be expelled, there must also be hundreds of billions of white holes doing the opposite. Yet, we have never found a single white hole in the cosmos. This has led some scientists to believe white holes do not belong to our universe but are instead gateways to another one. Matter consumed on this side gets released on the other side. Since black holes and white holes lie in separate universes, we cannot directly observe white holes from within ours. However, what's truly alarming is this: if white holes exist, they could be far more dangerous than black holes. Why are white holes more frightening than black holes? Because black holes have a safe zone. For example, the black hole closest to Earth, Gaia BH1, is about 1,500 light-years away, and even has a star orbiting around it. Matter only gets pulled in once it crosses the event horizon. If a safe distance is maintained, a black hole could even serve as a stable energy source, like a hypothetical artificial star. But if a black hole were replaced by a white hole, everything would change. White holes continuously eject matter and energy outward, producing intense radiation, like a never-ending supernova explosion. Any planet or star near a white hole would suffer catastrophic effects, making life or civilization impossible. Therefore, if we ever do discover a white hole, the first question wouldn't be, does it lead to another universe? But rather, is it heading toward us? Currently, scientists can confirm that a white hole is not a twin object born alongside a black hole. It is not a necessary consequence of a black hole, but instead requires extremely special physical conditions to form, conditions that no longer exist in our present-day universe. The deeper reason is that space-time in today's universe is already too stable. Whether it's a white hole or a wormhole, both could only have formed in the early universe, right after the Big Bang. At that moment, the universe had an extremely high temperature, and space-time was still flexible and tightly bound, like boiling liquid with random bubbles appearing in the pot. Only in this boiling environment could space-time anomalies like wormholes or white holes emerge. Some cosmologists even propose a bold hypothesis. The Big Bang itself may have been the result of a supermassive white hole spitting energy outward, and the cosmic inflation phase of the universe may have been its consequence. The matter it ejected was evenly distributed from the start, explaining why the current universe shows a relatively uniform distribution of galaxies in all directions. What does humanity truly need? Not black holes, but wormhole technology. Within the limits of current physics, wormholes are the only theoretical structure that could allow humans to travel dozens of light-years in a short time. Without them, even if we had spacecraft traveling at the speed of light, we still wouldn't be able to leave the Milky Way within a human lifetime, since its diameter is up to 180,000 light-years. Zooming out, there are at least 2 trillion galaxies in the universe, so why does only Earth seem to host life? This question leads to a particularly striking hypothesis, known as the strong anthropic principle. This hypothesis suggests all the conditions in the universe, from the galactic level to the solar system to Earth, were set up specifically to allow humans to exist. In other words, the universe wasn't a random place where humans happened to appear. The universe exists because of humanity. According to this theory, the reason why only Earth has life is because only Earth has the perfect conditions for humans to exist. Other planets lack such an environment, and therefore, life cannot develop. Not because the universe is too vast, but because humanity itself is that unique. However, this hypothesis carries an air of absolute destiny and is not widely accepted in the scientific community. Most astronomers still lean toward the likelihood that extraterrestrial life truly exists. We just haven't developed the technology to detect it yet. Just like in the past, scientists once believed the long channels on Mars were canals, built by an ancient civilization, until a few decades ago when we realized that Mars is a barren, desolate world. Single-celled organisms are common. Intelligence is rare. From a broader perspective, Simple life forms like single-celled microorganisms could be widespread in the universe. They don't require overly stringent environmental conditions, and even Earth, Mars, or primordial Venus might have once produced such life forms. However, only Earth has experienced an uninterrupted evolutionary process, progressing from simple to complex, from biological to intelligent life. The key condition for life to develop is, it requires billions of years of stability to evolve from single-celled to multicellular organisms and eventually to intelligence. Yet very few planets in the universe can provide such prolonged stability. A single nearby supernova explosion is enough to wipe out all nascent life on a planet. Any of these events could wipe out human civilization within a relatively short time. And these are some of the likely candidates for what's called the Great Filter in the Fermi paradox, the barriers that prevent civilizations from surviving long enough to reach interstellar scale. As for the existence of alien civilizations, they could appear with a flash of light-speed technology in the very next second, or perhaps they will never visit Earth at all. So why do scientists often say, if humanity is the only intelligent life in the universe, that is a terrifying thought? Because to date, astronomers have discovered over 5,400 exoplanets. Among them, dozens bear striking similarities to Earth, such as Kepler 452b and Kepler 22b. But all of these planets share one disappointing trait. There are no signs of life, nor any trace of intelligent civilizations. Even the most sensitive radio telescopes on Earth have never received a suspicious electromagnetic signal that might indicate alien existence. And if indeed this vast universe holds only us, then not only would humanity be profoundly alone, it also raises a much darker question. Are we truly wise enough to survive? All the observations we've made so far seem to point to the same conclusion. It's possible that humanity is the only intelligent life in the universe. But statistically, that seems almost impossible. Earth has existed for just 4.5 billion years, while the universe has a history of over 13.8 billion years. Even if the odds of intelligent life emerging are astronomically low, when multiplied across trillions of galaxies and stars, the number of potential civilizations should vastly exceed the population of Earth. From both a rational and emotional standpoint, it's hard to believe that humanity is alone in the universe. That's why some astronomers have proposed a hypothesis. The solar system, or perhaps even a large region of the Milky Way, might be deliberately isolated by higher civilizations, preserved as a kind of sanctuary for emerging life forms. In that scenario, human civilization is akin to fish in a pristine aquarium, or like a primitive tribe living in isolation on a remote island, constantly observed from afar by more intelligent beings, yet completely unaware. This could explain why, within the observable universe, everything appears so quiet. No electromagnetic signals from intelligent life, no alien spacecraft, and no confirmed visits to Earth. Even Earth, the fortunate planet, has undergone at least 5 major mass extinctions and numerous minor ones. From this, we can conclude, life, especially in its early stages, is extremely fragile in the universe. Even humanity today could be wiped out by an asteroid just a few dozen kilometers in diameter. Just as dinosaurs once went extinct, humanity today faces cosmic risks and uncertainties, notably the question of extraterrestrial life. In the quest to find alien civilizations, some astronomers have proposed monitoring CO2 levels in the atmospheres of distant planets. Typically, a planet's atmospheric CO2 remains stable unless significantly altered from within. Sudden changes could stem from 2 possibilities: large-scale volcanic eruptions like those on Venus, or the onset of industrialization similar to Earth, where civilization activities cause CO2 levels to spike. If the latter occurs, a rising CO2 graph would indicate that the planet is advancing technologically. This allows astronomers to infer the development level of an alien civilization. However, among the over 5,400 exoplanets discovered to date, none have shown abnormal CO2 increases. Considering that most of these planets are several hundred to several thousand light-years away, scientists can tentatively conclude that, At least in this region of the universe, humanity is the sole intelligent civilization. In other branches of the Milky Way, obscured by cosmic dust, we currently cannot observe in detail. Sending probes there isn't feasible either, as controlled nuclear fusion technology hasn't made breakthroughs, and current spacecraft speeds don't even reach 1/10 the speed of light. Probes can only operate within the solar system. Exploring the galaxy would take tens of thousands of years, rendering it practically meaningless. Stephen Hawking, the brilliant physicist, repeatedly warned that humanity should not actively contact alien civilizations. The renowned sci-fi novel, The Three-Body Problem by Liu Cixin, also presents the dark forest hypothesis, where all civilizations hide in silence, as any signal could lead to detection and destruction. If the universe truly operates this way, then the day we discover aliens could also mark the end of human civilization. Nevertheless, the journey to explore the universe continues. Recently, astronomers discovered a new star system, Kepler-90, located 2,545 light-years from Earth. Notably, this system also has 8 planets like our solar system, and its central star has a mass nearly equivalent to our Sun. In the universe, star systems with many planets are extremely rare, as most have only 1 or 2. Systems with 5 or more planets, like the solar system or Kepler-90, are nearly one of a kind. Interestingly, in such systems, the likelihood of life and civilizations emerging is higher. The more planets there are, the greater the chance that one or several fall into the habitable zone, where climate, light, and temperature conditions are stable enough for life to form. Data from the Kepler telescope indicates that Kepler-90 has 3 rocky planets, super-Earths, with masses and sizes larger than Earth but located in the habitable zone. These are named Kepler-90b, Kepler-90c, and Kepler-90I. The remaining 5 are gas giants similar to Jupiter and Saturn, though it's unclear if they have rings. Kepler-90 is only 2,200 light-years away, placing it and the solar system within the galactic habitable zone, not too close to the galaxy's center, filled with black holes and radiation, nor too far at the edges where matter is scarce. This positioning provides both systems with sufficient time and physical conditions for life to form and develop. However, the only limiting factor for Kepler-90 might be the lifespan of its central star. Currently, this star is about 2 billion years old, only half the age of the Sun, so its internal nuclear fusion reactions are still very intense, potentially affecting the long-term climate conditions of surrounding planets. The habitable zone around a star isn't fixed, but gradually moves outward over time as the star brightens and heats up. This shift might prevent planets in the Kepler-90 system from maintaining stable light and heat conditions over extended periods, hindering the formation and development of life. For instance, Kepler-90I currently orbits its star at just 0.1 astronomical units, AU, only 1/10 the distance from Earth to the Sun. Each orbit takes just 14 days, and its surface temperature reaches 400 degrees Celsius, a highly extreme environment. While we can't rule out the possibility of silicon-based life forms that can withstand high temperatures, for carbon-based life like ours, such harsh conditions are nearly uninhabitable. We often say that life is incredibly resilient, yet carbon-based life requires at least water and oxygen to survive. Even ultra-resilient organisms like the tardigrade, famed for surviving in outer space, still need a minimum amount of water and oxygen to function. As for the Kepler-90 system, scientists believe that the planets there likely lack liquid water. If any did exist, the James Webb Space Telescope, JW, would have already detected water vapor in the atmosphere. But so far, no such signs have been observed. Therefore, most astronomers agree that the Kepler-90 system currently does not host life. Let's look back at Earth, a planet born around the same time as the Sun. It wasn't until 3.8 billion years ago that Earth began forming the first single-celled organisms in the depths of the ocean. Meanwhile, the planets in the Kepler-90 system are estimated to be only around 2 billion years old, not enough time for biological evolution to begin. Perhaps in another billion years, When the light and temperature from the Kepler-90 star become more stable, the habitable zone planets will be able to retain liquid water, form oceans or subsurface seas, and potentially nurture the very first seeds of life. In the nearer future, as probes explore more planets within our own solar system, astronomers believe that signs of extraterrestrial life might actually be found on Mars. Once a potentially habitable planet around 4 billion years ago, Mars may have had a brief window to develop basic forms of life. However, all of this still requires confirmation, possibly in the future, when humanity finally sets foot on Mars, exploring its icy poles or underground lakes. If we do discover life there, we could conclude that life in the universe is far more common than we previously thought. And in that case, the reason we have never encountered any alien civilization might be explained in a simple, yet thought-provoking way. They are deliberately avoiding us. The Laniakea supercluster, home to over 100,000 galaxies. Could it be the cosmic monster humanity has yet to comprehend? In the Milky Way, our sun is nothing more than a tiny speck. But in the grander scale of the universe, even the Milky Way itself is hardly anything remarkable. According to astronomers, the Milky Way, the Andromeda Galaxy, and dozens of nearby galaxies form what's known as the local group. This local group is just a small part of a much larger structure, the Laniakea supercluster, which contains up to 100,000 galaxies, including our very own Milky Way. And beyond Laniakea, even larger cosmic structures exist, overlapping superclusters, vast galactic walls, and the knots in the web of the universe. The Laniakea supercluster is truly a cosmic monster, a massive structure composed of over 100,000 galaxies, stretching across 520 million light-years in diameter, making it one of the most significant anchor points in the observable universe. It is also a convergence zone for multiple cosmic walls, enormous chains of galaxies extending billions of light-years, interwoven like a giant spiderweb. Yet it wasn't until 2014 that astronomers first identified and named Laniakea. Before that, this region of space was simply noted as a faint hotspot on the cosmic microwave background map. Based on its position and massive scale, scientists have since constructed 3D maps of other superclusters and galactic walls across the observable cosmos. More importantly, they realize that no matter how massive it is, Laniakea and structures like it won't last forever. The reason lies in dark energy, a mysterious force that makes up about 70% of the universe's total energy and is accelerating its expansion. As the universe continues to expand at an ever-increasing rate, structures spanning billions of light-years like the Great Cosmic Wall and superclusters like Laniakea will eventually stretch and tear apart into smaller, isolated fragments. Laniakea will not be spared this fate. The only problem is, we haven't actually detected dark energy or dark matter directly. They only exist in theoretical models. Back in the early 20th century, Einstein introduced the concept of dark energy through a mysterious constant in his general theory of relativity, meant to maintain a static universe. But after Hubble discovered that the universe is expanding, Einstein promptly abandoned the constant, calling it the biggest blunder of his life. No one expected that, more than half a century later, astronomers would find evidence supporting the existence of dark energy, just as Einstein initially predicted. However, contrary to earlier expectations, the 70% proportion of dark energy is overwhelmingly large. It makes up nearly the entire universe. What we can see, all the galaxies, stars, planets, and cosmic dust, accounts for less than 5% of the entire universe. The rest is dark energy and dark matter, completely invisible to the naked eye, but with effects that can be felt through gravity and unseen interactions. Returning to Laniakea, if humanity is never able to build spacecraft capable of light-speed travel or open wormholes, then perhaps our civilization will never escape the boundaries of this supercluster. In fact, even the solar system alone, about 2 light-years in diameter, is already far too vast for humans to fully explore. Scientists estimate it could take tens of thousands of years for humanity to truly exploit all the resources within the solar system. Expanding beyond that to the Milky Way, which spans roughly 180,000 light-years, would require even more time, possibly on an unimaginable scale. If light-speed travel and wormholes forever remain out of reach, the operational range of human civilization might always be confined to just a few dozen light-years around Earth, or perhaps even less. The reasons are limited resources, combined with communication delays and coordination breakdowns that could cause space colonies to drift apart and follow separate paths, pushing human civilization toward fragmentation or extinction in the darkness of space. Are we at the center of the universe? One phenomenon that once puzzled scientists is this. Nearly all the galaxies we observe seem to be moving away from Earth. Does that mean Earth is at the center of the universe? From Newton to Einstein, most scientists once believed that the universe was static, unchanging over time. But in 1929, astronomer Edwin Hubble analyzed the redshift of galaxies and demonstrated that nearly all galaxies are receding from us, meaning the universe is expanding. By the late 20th century, new data from supernovae stunned the scientific community again by revealing the universe isn't just expanding, it's expanding at an accelerating rate. The culprit behind this acceleration is dark energy, which accounts for 70% of the entire universe. Even more astonishing, the farther a galaxy is from Earth, the faster it seems to be moving away. However, since light travels at a maximum speed of 300,000 kilometers per second, the light from extremely distant galaxies doesn't always reach Earth in real time. This gave rise to the concept of the observable universe, a spherical region of space centered around Earth, with a radius of about 46.5 billion light-years and a diameter of 93 billion light-years. This region is also known as the Hubble volume. Within this region, because we are observing from Earth in all directions, it appears as though most galaxies are moving away from us. But on a cosmic scale, Earth is not the center. It is merely a random point of observation. According to measurements from the Hubble Space Telescope, the current rate of expansion is approximately 67 kilometers per second per 3.26 million light-years, a relatively modest speed. On scales of several million light-years, gravity can still dominate, which is why the Andromeda Galaxy is still on course to collide with the Milky Way in the future despite cosmic expansion. However, for galaxies tens of millions of light-years away or more, the rate of expansion eventually overcomes all gravitational forces, causing them to move away from Earth and gradually fade beyond our reach. Specifically, if a galaxy is more than 14.5 billion light-years away, the rate of expansion between us exceeds the speed of light. In that case, light from that galaxy will never reach Earth, meaning it has moved beyond our light cone, and in theory, no longer exists in the universe we can access. If the estimate that dark energy comprises 70% of the universe is accurate, then the expansion will only accelerate. Eventually, all galaxies will slip beyond Earth's light cone, leaving the Milky Way as the only galaxy remaining in our observable universe. And not only that, within the Milky Way, the distances between stars will also grow due to superluminal expansion, potentially leading to the galaxy's complete disintegration. As the universe's matter density drops to extremely low levels, a time may come when even planets, stars, and atoms are stretched and torn apart, a scenario known as the Big Rip. However, if this ever happens, it would be trillions of years in the future, far beyond our current concerns. In reality, the threats most immediate and relevant to humanity are far closer to home. The impending collision between the Milky Way and Andromeda in about 3.7 billion years, the Sun expanding into a red giant in roughly 5 billion years, the ongoing global climate crisis, or the risk of asteroid impacts. Across hundreds of millions of light-years, trillions of galaxies are influenced by dark energy and dark matter, expanding and flowing along cosmic walls, the vast filaments of the universe. However, like light, gravitational influence cannot exceed the speed of light. Scientists believe many large structures in the universe have already been torn apart by superluminal expansion, even though the galaxies within them remain unaware, continuing their motion by inertia. For instance, the Milky Way's journey toward the Great Attractor may be a voyage with no real destination. An intriguing theory proposes that the local bubble, or the Oort cloud, may be responsible for blocking extraterrestrial signals. These structures may act as cosmic filters, shielding us from organized electromagnetic waves sent by intelligent civilizations, allowing only random cosmic noise to reach Earth. This mechanism could be how advanced civilizations protect primitive ones, much like how humans establish ecological preserves to shield isolated tribes from premature contact with modern technology. Perhaps, only when humanity builds light-speed spacecraft and escapes the solar system will extraterrestrial civilizations formally reveal themselves and communicate with us. For now, whether it's Voyager 1 or Earth's faint radio signals, all are too slow and too weak, eventually lost in the cosmic background noise. In short, whether it's the local bubble or the Oort cloud, these are regions of space currently beyond our reach. In the near future, humanity's practical reach will remain limited to just 3 worlds: Earth, the Moon, and Mars. Terraforming and colonizing even these 3 could take thousands of years. Fully developing the entire solar system may take tens of thousands more. The final question is, will there be another technological leap in the future, where, in just a few decades, humanity achieves more than we've managed in millennia? No one can say for sure. Everything depends on when modern physics will hit its limits. Only through true breakthroughs might we welcome the next Einstein, someone who will usher in a whole new era of physics and technology. But even if we had a spaceship that could travel 1 light year per second, how long would it take to escape the universe? At light speed, 300,000 kilometers per second, you could circle Earth's equator 7.5 times in 1 second. Some scientists even suggest that only when humanity develops light-speed travel will extraterrestrial civilizations reveal themselves, finally offering us a glimpse of the greater truths of the universe. Putting aside these grand hypotheses, many astronomers believe that extraterrestrial life may be much closer to us, at least in the form of microorganisms. They suggest that several places in our solar system, such as the icy polar regions of Mars or the moons of Jupiter and Saturn, may offer environments even more stable than some locations on Earth. Microbes or single-celled organisms could survive and evolve in those habitats. The problem lies in our current technological limitations. We simply don't yet have the precision or capabilities to detect life in such remote and harsh environments. Only when humans set foot on Mars, or when we send advanced probes to the moons of Jupiter and Saturn, will we truly have a chance to uncover signs of life beyond Earth. Even more intriguingly, Mars, not Earth, might have been the first planet in the solar system to harbor life, around 4 billion years ago. At that time, Mars had liquid water and an atmosphere, while Earth was still a scorching, molten planet. It was only after Mars lost its magnetic field, allowing the solar wind to strip away its atmosphere, that the planet became the dry, barren world we see today. Notably, scientists have discovered Martian meteorites on Earth, such as those found in Antarctica, and some believe that life on Earth may have originated from Mars. Alternatively, organic molecules delivered by comets striking Earth billions of years ago may have sown the seeds of life in our oceans. Still, all of this remains hypothetical. Only by landing on Mars and conducting a global exploration will we have a real chance of finding remnants of ancient life on the red planet. If humanity is alone in the universe, if in the end, humanity truly is the only intelligent species in the entire universe, that would mean we have no reference point, no example to follow for how civilizations might evolve into the far future. We would be forced to chart our own course in the darkness of the cosmos, step by step. In a more extreme interpretation, the entire universe could be a simulation, and we are simply subjects being observed. Currently, the solar system lies along the Orion arm of the Milky Way, and what we perceive as the Milky Way in the night sky is actually a dense band of gas and dust that blocks our view of the galactic center. Even telescopes like Hubble or Webb cannot see through this dusty veil. Only X-ray and radio telescopes can penetrate the dust, allowing astronomers to study the star distribution in the galactic core, and these discoveries continue to reshape our understanding of the universe every day. All stars in the center of the Milky Way orbit an invisible gravitational source. Astronomers have calculated that this object's mass is 4.4 million times that of the Sun. It can only be a supermassive black hole. This object is now known as Sagittarius A star and is considered the king of black holes within the Milky Way. Surprisingly, supermassive black holes aren't entirely dark and invisible, as many believe. On the contrary, they are incredibly luminous because of the accretion disks surrounding them, where matter is torn apart as it falls inward, emitting intense light and heat. In certain conditions, black holes and stars alike could even provide the energy necessary to sustain life. In actual telescope images of Sagittarius A star, one can see a glowing reddish-orange halo encircling the dark core. This is the bright accretion disk. Although the black hole itself is invisible, scientists can confirm its existence indirectly through this surrounding radiation. The galactic center isn't home to just one black hole. It also contains numerous globular clusters, concentrations of massive aging stars. After undergoing supernova explosions, these stars leave behind stellar black holes, which now orbit around Sagittarius A star. This is one reason why the Milky Way's center is so radiant and brilliant. The Milky Way, a spiral of gravity and light. The entire Milky Way consists of multiple spiral arms and around 400 billion stars, all orbiting the galactic center, where the gravitational pull is strongest. Sagittarius A star, along with the surrounding stellar black holes and star clusters, forms a massive gravitational anchor that prevents the galaxy from collapsing or breaking apart. According to Einstein's general theory of relativity, once something crosses a black hole's event horizon, it can never escape. The escape velocity exceeds the speed of light, which is impossible in our universe. However, theory also predicts that matter falling into a black hole might eventually be expelled through a theoretical counterpart, a white hole, a celestial object that emits matter but cannot absorb any. Unfortunately, just like wormholes, there is no observational evidence that white holes exist in nature. Perhaps the universe's current space-time structure is simply too stable to allow such exotic objects to form. At present, the nearest black hole to the solar system is about 1,500 light-years away, posing no immediate danger. What concerns astronomers more are rogue black holes, those not fixed in any stable orbit. If such a black hole were to drift within 1 light-year of the Sun, it could destabilize the entire solar system, potentially ejecting Earth from orbit and turning it into a true rogue planet. That said, such a scenario is unlikely in the near future. At least for the next few hundred years, humanity still has precious time to prepare, and possibly even leave the solar system to find new homes elsewhere in the Milky Way. Some physicists have proposed that humanity might one day create microscopic black holes using particle accelerators, tapping into them as a source of limitless energy. However, according to Hawking radiation theory, these tiny black holes would evaporate almost instantly, meaning that energy extraction from black holes remains theoretical and currently impractical. The Fermi paradox remains. If human civilization continues progressing at its current pace, we might spread across the entire Milky Way in as little as 300 million years. But the great unanswered question remains: why have we still not detected any extraterrestrial civilizations? In scientific circles, debate over the existence of alien civilizations has persisted for centuries. Today, the majority of scientists lean toward the idea that other civilizations likely exist, but they are simply too far away, and our technology is still too primitive to detect them. A smaller group believes that humanity is truly alone, that we are the sole intelligent species in the entire cosmos. Yet, Advances in astronomy over the past few decades have shown that Earth, the solar system, and even the Milky Way hold no special place in the universe. Among the 2 trillion galaxies we can currently observe, each contains hundreds of billions of stars and planets. This means that somewhere, in the vastness of those countless worlds, the emergence of life, as it did on Earth, could very well be repeated. Even if the odds of a civilization like ours forming were 1 in a trillion, when multiplied by the staggering number of planets in the universe, the number of possible extraterrestrial civilizations should still exceed Earth's current population by far. Therefore, the real question is no longer, do they exist, but rather, why have extraterrestrial civilizations never left a trace in the universe? And why have they never visited the solar system? From a temporal perspective, in just 10,000 years, humanity has evolved from the Stone Age to the modern technological era. At a steady rate of development, it could take only another 300 million years for human civilization to expand across the Milky Way, reaching every potentially habitable planet. So if a civilization had emerged just 300 million years before us, they should have already dominated the entire galaxy by now. And yet, 13.8 billion years after the Big Bang, we still see no evidence of any advanced extraterrestrial civilization. It's as if they've completely vanished, or that humanity is currently the most advanced civilization in the cosmos, while others are still in their stone ages. This eerie contrast lies at the heart of the Fermi paradox. Where are they? One of the most thought-provoking explanations is the dark forest theory. According to this theory, every civilization understands that resources in the universe are finite, while the expansion of civilizations is potentially infinite. Therefore, they all choose silence, concealment, and the readiness to destroy any civilization that exposes its location. Another hypothesis suggests that the solar system, or even the entire Milky Way, might be a low-tech preserve, deliberately set aside by more advanced civilizations. Only when humanity reaches a certain technological threshold, such as achieving light-speed travel, will these civilizations reveal themselves and make contact. What's fascinating about this theory is that it aligns perfectly with the Copernican principle, also known as the non-special principle, that Earth and humanity are not the center of the universe, nor the protagonists of any grand narrative. We are merely one among billions of ordinary beings scattered across the cosmos. In summary, while the search for intelligent civilizations remains elusive, the discovery of extraterrestrial life, at least microbial, has never felt closer. Astronomers believe that under Mars' surface, or near its polar ice caps, simple microorganisms might exist. Likewise, the subsurface oceans beneath the icy crusts of Jupiter's and Saturn's moons may be home to primitive life forms. At the moment, such life, if it exists, may be rudimentary. But in the future, as humanity continues to explore the solar system, we may one day stumble upon alien life. There's even a chance that an alien civilization could suddenly appear near Earth in an unexpected moment. In the pursuit of such discovery, astronomers have identified a mysterious structure between the Sun and the center of the Milky Way, a bubble of gas surrounding the solar system that may hold secrets yet unknown. This structure is called the local bubble, a vast region approximately 1,000 light-years in diameter. It acts as a natural insulating layer, separating the Sun and dozens of nearby stars from direct interaction with the broader interstellar environment of the Milky Way. Interestingly, about 5 million years ago, the Sun entered this bubble purely by chance as it orbited the galactic center. And today, it sits precisely at the bubble's center, just in time for astronomers to study it. Unlike the dazzling nebulae seen in astronomical images, the local bubble is actually the remnant of a supernova explosion that occurred around 14 million years ago. The blast disrupted and dispersed the surrounding dust cloud, expanding it from an initial diameter of about 4 light-years to its current size. The solar system entered this region afterward, With an orbital velocity of about 220 kilometers per second around the galactic center, astronomers estimate that in another 5 million years, the Sun will exit the local bubble and return to the real space of the Milky Way. What lies ahead then? A pending supernova? A rogue black hole? At present, we have no idea. On the cosmic scale, all celestial bodies are in constant motion. The Milky Way itself is traveling toward the Great Attractor at a velocity of 550 kilometers per second. However, the early Milky Way looked nothing like what we see today. Over more than 10 billion years of evolution, the Milky Way has collided with many neighboring galaxies, altering its structure and redistributing stars. In about 3.8 billion years, it is expected to collide with the Andromeda Galaxy, initiating yet another major transformation. Each of these collisions reshapes the galaxy and changes the density of stars throughout. Though the Milky Way currently has a barred spiral structure, it may eventually become an elliptical galaxy or even lose any recognizable shape altogether. One thing is certain: the number of stars in the Milky Way continues to increase. It's estimated that the galaxy currently contains between 100 and 400 billion stars, distributed along multiple spiral arms, all orbiting the supermassive black hole Sagittarius A* at the center. But this distribution is far from uniform. In the galactic core, star density can reach hundreds of thousands of stars per cubic light year. In contrast, in the more suburban areas like the Orion Arm, where the Sun resides, the average distance between stars is about 4 light years. In theory, the denser the concentration of stars in a given area, the greater the probability of life and civilization emerging. For this reason, astronomers have repeatedly sent signals toward globular clusters near the center of the Milky Way, hoping to detect traces of extraterrestrial civilizations. The most famous message ever sent into space was the Arecibo message. However, in recent years, studies of the habitable zone within the Milky Way have revealed that, although the galactic center is densely packed with stars, most of them are old stars with intense radiation and roaming black holes, conditions that are highly unfavorable for the formation and evolution of life. In contrast, stars located in the suburban zones of the galaxy, like our Sun, a yellow dwarf, are far more likely to host life. These stars tend to have longer lifespans, more stable activity, and are less affected by black holes. In such environments, inorganic compounds have enough time to evolve into organic ones, and eventually develop into living organisms, even intelligent civilizations. The Drake equation, a famous tool used to estimate the number of extraterrestrial civilizations, originally suggested that the Milky Way could host dozens of them, based on the assumption that our galaxy contains around 100 billion stars. At that speed, in just one day, you could catch up with Voyager 1, which has been traveling for 47 years. 1 year would be enough to exit the solar system. But with a superluminal craft traveling 1 light-year per second, it would take just 1 second to leave the solar system, 4 seconds to reach Proxima Centauri, the hypothetical home of the Trisolarans, 8 seconds to reach Sirius, 11 minutes to the Cat's Eye Nebula, 2 hours to the Pillars of Creation, 24 hours to exit the Milky Way, 1 month to reach the Andromeda Galaxy, 2.54 million light-years away, 16 years to cross the Laniakea supercluster, and 1,500 years to reach the edge of the observable universe. But if the observable universe is only 1/250 of the entire cosmos, then even at such unimaginable speeds, we still wouldn't be able to reach its true edge. In reality, the universe may have no edge at all. According to current measurements of spatial curvature, the universe may be flat and infinite. However, if future findings confirm curvature, the universe could be a closed 4-dimensional hypersphere, like the surface of a sphere in 3-dimensional space, but on a higher dimensional scale. Beyond that structure, parallel universes, or a multiverse, may exist. But there's a fundamental issue. To escape the universe, what's needed is not just speed, but a direction of travel in a higher spatial dimension. Just as a rocket must ascend vertically to escape Earth's gravity, future science will need to discover a pathway into the 4th spatial dimension in order to truly break free from our universe. Without that, even with superluminal speed, a spacecraft would simply loop back to its starting point, like circling the globe without ever leaving it. When it comes to technologies that could allow travel across dozens of light years in a short time, many people often think of wormholes, space-time tunnels, predicted by Einstein's general theory of relativity. These hypothetical structures could connect two distant points in space-time directly. Although no wormholes have been observed, there are reasons to believe they might exist, just like black holes, which were once purely theoretical. However, according to Stephen Hawking and many other physicists, natural wormholes could only have formed during the chaotic early stages of the Big Bang, when space-time was unstable, like bubbles in boiling water. Once the water cooled, meaning the universe underwent superluminal inflation and stabilized, those wormholes would no longer be sustainable. To create artificial wormholes in the future, humanity would need exotic matter or negative mass, concepts still far beyond our experimental and theoretical reach. Given the improbability of both superluminal travel and wormhole construction, some scientists suggest that civilizations across the universe may find it virtually impossible to reach one another, or even to fully explore their own galaxies. The maximum expansion range of any civilization might be limited to just a few dozen or 100 light years. Once the resources within that range are exhausted, the civilization may collapse and disappear from the universe. For humanity today, we still face numerous existential threats that could wipe out our civilization. Asteroid collisions, gamma-ray bursts, nearby supernovae, or rogue black holes entering the solar system. These risks are what the Great Filter Hypothesis refers to in the Fermi paradox, potential barriers that most civilizations fail to overcome in order to endure long-term. So in the end, how long can human civilization survive, and how far can it go in this vast universe? The answer remains for the future to decide. No one knows. If the universe has billions of stars, why is the night sky still dark? In 1823, astronomer Heinrich Olbers posed this very question. He theorized that if the universe were infinite and static, then light from countless stars would eventually illuminate the entire night sky. But today, we know that the universe is expanding at a rate that exceeds the speed of light. Light emitted from distant stars simply cannot reach Earth, because the space-time between us and those stars is expanding faster than the light can travel. As a result, light from stars beyond about 14.5 billion light-years will never reach us. They are forever in transit, but will never arrive. Looking deeper, astronomers have observed around 2 trillion galaxies, yet 98% of them currently lie beyond the 14.5 billion light-year boundary. In other words, we only see them as they appeared in the past. Because they've receded beyond Earth's light cone, we've lost all causal contact with them. No information can reach us from them, because nothing can travel faster than light. In fact, scientists believe that if the universe continues to expand at its current accelerating rate, more and more stars will become isolated from Earth. Eventually, the entire universe, except for a few 100 billion stars within the Milky Way, will be pushed beyond our observable horizon. The end result? A steady decline in matter density, followed by the eventual disintegration of large-scale structures like cosmic walls and superclusters, then the Milky Way, the solar system, and even Earth itself. A universe that may shrink again? However, Nobel laureate Professor Roger Penrose suggests that the universe may not expand forever. He theorizes that at some point in the future, cosmic expansion will slow, then stop, and eventually reverse under the pull of gravity. As that happens, galaxies will begin to move closer to Earth, and we will be able to observe more stars once again. This contraction would increase the universe's matter density until everything collapses into a singularity, a point of zero size. From there, a new Big Bang would occur, giving birth to a brand new universe. This cyclical universe theory offers a compelling explanation for both the origin and fate of our cosmos. Unfortunately, current observations show no sign that expansion is slowing. Dark energy, which makes up 70% of the universe's total mass energy, continues to dominate. It overwhelms gravity with its repulsive force, causing the universe to expand faster and faster. And these ever-growing distances might be the real reason we haven't found alien civilizations. Even with spacecraft that travel at light speed, or tools like gravitational waves and neutrino detectors, nothing can exceed the speed of light. This means we cannot transmit or receive signals across the entire universe, or even reliably across the Milky Way. That's why neither Voyager 1 nor Earth's radio telescopes have been able to make contact with alien civilizations. Of course, wormhole technology might one day allow humanity to travel faster than light. But here's the catch. To build the first wormhole gate, we still need to physically get to the destination using conventional means. That makes the idea of building a wormhole network across the galaxy nearly impossible. In the end, we may simply grow old and die within a tiny patch of space, just a few light years across. For human civilization, that patch might include the entire solar system, or perhaps a handful of nearby star systems like Proxima Centauri, but at best, we may never reach beyond a few dozen light years. Have you ever asked yourself, why must all forms of life ultimately die? If you were to ask a physicist, what is the most hopeless law in the universe, they would almost certainly answer, the law of entropy, also known as the law of increasing disorder. Because this law predicts the eventual fate of all matter in the universe. Even Albert Einstein once referred to it as the first law of all physics. But what is entropy, exactly? Simply put, entropy measures the level of disorder within a closed system. For example, compare an intact glass with a shattered one. The broken glass has a higher level of disorder, or in other words, higher entropy. Similarly, a tidy room has lower entropy than a messy one. And the key point is, entropy always increases. It cannot be reversed. You can't make a shattered glass reassemble itself, or a chaotic room clean itself up. Even if you actively clean or restore something, the process itself generates additional entropy elsewhere, so the total entropy of the overall system still increases. Physicist Erwin Schrödinger once argued that life, at its core, is a structure of low entropy, and it survives by consuming negative entropy, in other words, seeking order. When life first emerged from Earth's primordial oceans, it had to constantly increase its internal organization, or else it would be overwhelmed by the chaotic environment. The drive toward order led to evolution, from simple to complex, from single-celled organisms to multicellular beings, and from primitive life to highly organized organisms. But even now, 3.8 billion years later, humans, the most organized life form on Earth, still cannot escape the grip of increasing entropy. Because entropy's rise is an inevitable law of the universe. Actions that consume negative entropy, such as learning, physical training, and technological development, are all efforts that locally reduce disorder. But since they go against the natural flow of entropy, they are inherently difficult, especially for the human brain. That's why people often struggle to maintain discipline, keep learning, or improve themselves. These efforts are literally fighting against entropy. It's not just life, celestial bodies also obey the law of entropy. For instance, the Sun is now a stable star, but in about 5 billion years, it will expand into a red giant and later become a planetary nebula, a more disordered state. Even black holes, which seem eternal, will eventually lose mass due to Hawking radiation and evaporate into nothingness. From atomic particles to the entire cosmos, nothing lasts forever. Everything is moving toward dissolution under the reign of rising entropy. If time stretches long enough, all stars will burn out, all black holes will evaporate, and the universe will descend into a cold, dark void for eternity. That's why Einstein called entropy the #1 law of physics, a principle that can never be overthrown, like an unchangeable line of code in the fabric of reality. Can entropy be reversed? That depends on whether our universe is truly a closed system. If parallel universes or a multiverse truly exist, then in theory we might be able to receive low entropy energy from other universes, rekindling the light and warmth of stars, sustaining life and civilization. But if this universe is all there is, then within a completely isolated system like this, entropy will only continue to rise, and the ultimate fate will be the heat death of the cosmos. In this grim scenario, if human civilization survives until the end of the universe, we will likely perish alongside the last fading star. When the remaining matter can no longer form new stars and no new energy sources remain, humanity will no longer be able to endure the frigid darkness of the dying universe. Fortunately, the heat death caused by entropy is trillions of years away. We have only lived through a fleeting moment in that immense timeline. The saying, "Heaven and earth are vast, the universe is boundless," is for us still just a philosophical concept. So within the Milky Way, one of the first galaxies in the cosmos, could it really be that humanity is the only civilization core? The evolution of the Milky Way, one of the oldest galaxies. As the parent system of the solar system, the formation and evolution of the Milky Way has long fascinated astronomers. After analyzing around 250,000 ancient stars near the galactic center, scientists now estimate that the Milky Way is about 13 billion years old, nearly the same age as the universe itself, 13.8 billion years. That makes it one of the earliest galaxies to have formed. If the actual number is 4 trillion stars, this estimate should be multiplied many times over. However, American geologist Dr. Stern has recently argued that the Drake equation is overly simplistic, failing to account for the critical role of continents in the development of life and civilization. Specifically, for a planet to develop a carbon-based intelligent civilization, it must simultaneously possess both oceans and stable continental landmasses. Oceans serve as the cradle for primitive life and complex cells, while continents provide the necessary resources for life forms to evolve into technological civilizations. Only civilizations based on continents can exploit resources, develop technology, and ultimately reach out into space. A planet covered entirely by ocean might still produce primitive life or even low-level civilizations, but they would never be able to harness fire, the foundational element for technological advancement. As a result, they would never achieve the status of a spacefaring civilization. Ultimately, Dr. Stern estimates that only about 0.02% to 1% of Earth-like planets in the Milky Way have both continents and oceans, and merely 0.003% to 0.2% have the potential to produce intelligent civilizations. These figures are far lower than the optimistic estimates of the Drake equation. In fact, among the 5,000-plus exoplanets discovered to date, it's very likely that none harbor life at all. Feathers eventually fall to the ground. So how can Earth, massive as it is, weighing an estimated 60 sextillion tons, float freely in space? In 1798, at the age of 67, Henry Cavendish calculated the gravitational constant g and used it to estimate Earth's mass at approximately 60 sextillion tons, 60 times 10 to the power 4 kilograms. By conventional thinking, such a heavy object should be supported by something even heavier. Otherwise, it should fall. Yet for decades, photos from space have consistently shown Earth seemingly suspended in the cosmos. Not just Earth, all the planets in the solar system, and even entire galaxies, appear to float effortlessly in the dark void, as if they have no weight at all. But according to Albert Einstein, no object in the universe truly floats. Instead, it is space-time itself that supports all massive objects. In places invisible to the naked eye, space-time is bent or warped by celestial bodies. The degree of curvature depends on their mass. The direct result of this warping is that smaller mass objects are drawn toward larger ones, such as the Moon orbiting Earth, Earth orbiting the Sun, and the solar system orbiting the center of the Milky Way. Orbital motion is a manifestation of curved space-time and the physical expression of gravitational force. Looking deeper, we realize that orbiting a massive celestial body is essentially a form of falling toward it, but never quite falling into it, thanks to horizontal velocity. In other words, Earth isn't truly floating in space. It is constantly falling toward the Sun, but due to its perfect curved trajectory, it never makes contact. Since the Sun holds 99.86% of the solar system's total mass, its gravitational pull is enormous. Nevertheless, just as an artificial satellite needs only 11.2 kilometers per second to orbit Earth without falling, Earth, traveling at around 30 kilometers per second, generates enough centrifugal force to counteract the Sun's gravity. Moreover, in the vacuum of space, where resistance is virtually non-existent, Earth can maintain this speed for an extended time, allowing it to orbit the Sun indefinitely without being pulled in. This also explains why planets closer to the Sun must move faster in their orbits. Only at high speeds can the centrifugal force balance the Sun's pull. If a planet moved too slowly, it would be drawn into the Sun. Conversely, distant planets like Pluto need only a modest velocity to maintain orbit, as the Sun's gravitational pull is much weaker at such distances. From artificial satellites to the International Space Station, maintaining orbital speed and altitude is essential. Otherwise, they would gradually descend and ultimately fall back to Earth. That's why space stations regularly perform orbital boosts to stay aloft. At its core, the universe resembles a giant matryoshka doll. The Moon orbits Earth, Earth orbits the Sun, the solar system orbits the supermassive black hole Sagittarius A Star at the center of the Milky Way orbits the center of mass of the Virgo supercluster, and this supercluster in turn orbits the Great Attractor. From the smallest planet to the largest galaxy clusters, the universal law of motion is the same. Everything is caught in the cycle of gravitational forces, creating continuous, nested orbital motions. This is precisely what Einstein's general theory of relativity describes. Matter tells space-time how to curve, and curved space-time tells matter how to move. Unfortunately, in the field of gravity, a contradiction exists between general relativity and quantum mechanics. Quantum mechanics suggests that gravity arises from the exchange of hypothetical particles called gravitons. If one day humans discover and manage to control gravitons, we might hold in our hands the technology of anti-gravity. However, up until now, gravitons have yet to be found, which implies the existence of a theory more advanced than both quantum mechanics and general relativity. This is exactly what Einstein longed for his whole life: the unified theory, or theory of everything. Perhaps a few hundred years from now, modern physics will, like classical physics, reach the limits of development. And then, a genius like Einstein may emerge, leading human civilization into an entirely new era. Dinosaurs ruled the Earth for over 160 million years. So why didn't they develop a dinosaur civilization? As the pinnacle of reptiles, dinosaurs first appeared during the Triassic period, about 240 million years ago. However, their true explosion happened after the extinction event at the beginning of the Jurassic, around 200 million years ago. From that point until the asteroid impact 65 million years ago, dinosaurs ruled the Earth for approximately 160 million years. During that time, many types of dinosaurs existed, from giant carnivores like T-Rex, massive herbivores like Brachiosaurus, to small ones like Troodon, feathered species, and flying dinosaurs, pterosaurs. However, many of the familiar dinosaurs did not live at the same time, and only a few had the potential to evolve into a civilization. Troodon, a small dinosaur that lived in flocks, with developed forelimbs and a relatively large brain, is considered the most promising candidate. This species appeared near the end of the dinosaur era, and some biologists believe that if the asteroid had not struck Earth 65 million years ago, Troodon might have continued evolving its brain, developing complex social behaviors and establishing a hierarchical system, the foundation of a true civilization. If events had unfolded differently, dinosaurs might have evolved their own civilization. They had the capacity to become bipedal, thereby freeing their forelimbs, leading to a form resembling reptilian humanoids. Unfortunately, fossil records to date show that their brains were far inferior to those of humans. The nervous systems of dinosaurs were quite simple. Among them, the most intelligent dinosaur is believed to be Troodon from the Dromaeosauridae family, but even its intelligence was insufficient for complex thinking. It could even be said that, although dinosaurs evolved over 100 million years into many different species, the differences in brain structure between them were minimal. From Tyrannosaurus rex to Troodon, their intelligence was still very limited. This reflects a deeper principle of natural selection. At that time, dinosaurs had almost no natural enemies. They didn't need to develop advanced brains to survive. In contrast, the small mammals of that era, our ancestors, constantly had to adapt to a changing environment. Paleontological findings show that right after the fifth mass extinction event over 60 million years ago, surviving small mammals began evolving rapidly. They started eating fruit and living in trees, honing their ability to perceive three-dimensional space, developing stereoscopic vision, and increasing the dexterity of hands and fingers. Most importantly, they were highly social, living in groups and coordinating collective actions. This process continued until around 6 million years ago, when the East African Rift split two groups of apes. One group ended up in an area without trees, the vast grasslands of Africa, and had to begin walking on two legs. These were the first ancestors of modern humans. The rest of the story is something most of us already know. Humans began using tools, discovered fire, and cooked food, helping their brains to grow further. From there, human civilization gradually took shape. When we look back on the evolutionary history of humankind, we realize that it was harsh living conditions that drove the brain to evolve. By contrast, dinosaurs did not face such survival challenges, so they had no need to evolve higher intelligence. In reality, after the fifth mass extinction, the remaining feathered dinosaurs adapted to the new environment and evolved into modern birds such as chickens, ducks, and geese. Nevertheless, we can be certain that humans today are still evolving slowly. In the future, when humans leave Earth and live in microgravity environments in outer space, the next generation may grow taller on average than people on Earth. As humans migrate and colonize planets like Mars or the Moon, they will change to adapt to completely new environments. These changes will still be within the limits of physiological adaptation. However, we cannot rule out the possibility that in the future, humans may have mechanical body parts, or even become half-human, half-machine beings. Astronomers tell us the universe is expanding faster than the speed of light. So what lies beyond the universe? As of now, the region of space more than 14.5 billion light-years from Earth has already begun expanding at superluminal speed. Galaxies beyond this range will never have their light reach Earth. Within the observable universe, which has a diameter of about 93 billion light-years, there are at least 2 trillion galaxies, and 98% of them are beyond the 14.5 billion light-year boundary from Earth. In other words, Earth is essentially isolated from most of the universe. One day, in the observable universe, besides the Milky Way, we will no longer see any other galaxies. The concept of the observable universe is actually a limit defined by the speed of light, while the universe itself continues to expand faster than light. The universe we observe is merely a special region within a much larger whole. And we are not alone in this. Any civilization in the cosmos will have its own observable universe. Some of those regions might even overlap or intersect with ours. Therefore, astronomers believe that beyond the part of the cosmos we can currently observe, countless galaxies and structures still exist, similar to what the Hubble Space Telescope has captured from deep space. In other words, there's nothing fundamentally different out there. We just can't see it yet. As for the actual scale of the entire universe, scientists estimate it could be about 250 times larger than our observable universe. And due to the ever-accelerating expansion of space-time, the extent of the universe continues to grow without end. However, from Albert Einstein's perspective, the true structure of the universe might be a four-dimensional hypersphere, a spherical space that is finite but has no edge in the way we understand three-dimensional space. Just like Earth's round surface has no boundary, you can keep going without ever reaching a wall, unless you move in an entirely new direction. the perpendicular dimension, the fourth dimension, to exit our familiar space and perceive the true edge. Therefore, to exit the three-dimensional universe we currently inhabit, humans may need a spacecraft capable of traveling at the speed of light, similar to how rockets on Earth must reach the first cosmic velocity to escape the planet's gravitational pull. Another hypothesis proposes that the universe may be an infinite flat plane with no endpoint. In such a case, since the speed of light is an insurmountable limit, even if we had spacecraft that traveled at light speed, we would still be unable to fly beyond the universe or perceive its boundaries or overall shape. In this infinite universe model, because the total amount of matter is finite, as the universe continues to expand, the matter density will continually decrease. The final consequence of this process is known as the Big Rip. In that scenario, all large structures in the universe, such as galaxies, stars, and planets, will be torn apart into smaller components, and eventually, even atoms will be destroyed. According to current observations, the largest structures in the universe are the cosmic walls. These enormous structures are interconnected to form what is known as the cosmic web. Within that web, superclusters like the Laniakea supercluster serve as major intersections. Our Milky Way is just a tiny part, approximately 1/100,000th of Laniakea. Compared to this structure, the solar system and even Earth are mere specks of dust. Interestingly, when viewed at the largest cosmic scale, the distribution of galaxies in space bears a striking resemblance to the way neurons are arranged in the human brain. This similarity has led some to suggest that the universe may be a giant brain, a living, thinking entity. However, with light speed fixed at 300,000 km per second, any thoughts of the cosmic brain would occur extremely slowly, perhaps requiring tens of billions of years to become self-aware. Thus, the question, what lies beyond the universe, remains a mystery with no definitive answer. Perhaps in the future, scientists will develop more advanced telescopes to pursue the answer. Or perhaps even until humanity completely disappears from the cosmos, that question will remain eternally unresolved. Currently, according to the Kardashev scale, a system for measuring levels of cosmic civilization, humanity is only at level 0.73. This means we have only partially harnessed the energy available from our own planet, Earth. A Type 1 civilization can fully control the energy of its planet. Type 2 can harness the energy of an entire star, like the Sun. And Type 3 is truly astonishing, capable of controlling the energy of an entire galaxy. If humanity's energy consumption continues increasing at a rate of 3% per year, we may reach Type 1 status within approximately 200 years. At that stage, we would be able to fully exploit all energy sources on Earth, from wind and solar energy to controlled nuclear fusion. At that point, we could not only regulate Earth's climate, but also build large-scale space cities, establish small research stations on the Moon and Mars, and explore the entire solar system. However, evolving from a Type 1 to a Type 2 civilization may require tens of thousands of years. The clearest hallmark of a Type 2 civilization is its ability to construct a Dyson sphere, a megastructure that encompasses an entire star, such as the Sun, capturing all emitted light and heat with zero loss. We should understand that, in just 1 second, the Sun emits enough energy to sustain human civilization for millions of years. The amount of solar energy Earth currently receives is only about 2.2 billionth of the Sun's total output. Therefore, a civilization capable of building a Dyson sphere would possess an almost limitless energy source, since all of a star's light and heat could be collected, stored, and transformed into electricity or other usable energy. But the major issue is this. The Sun accounts for 99.86% of the total mass of the entire solar system. The remaining mass is spread across the planets. This makes the construction of a Dyson sphere a nearly impossible feat. Scientists estimate that to gather enough material to construct a Dyson sphere surrounding the Sun, humanity would need to dismantle Mercury and Venus entirely. However, if this were to happen, it would severely disrupt the gravitational balance of the solar system, possibly making Earth uninhabitable for human life. Nevertheless, once humanity masters the energy of a star, a Type 2 civilization could use that star system as a springboard to rapidly expand throughout the Milky Way. In just tens of thousands of years, or even sooner, through exponential development, humans could leave their mark on hundreds of billions of star systems in the galaxy. By then, technologies like wormholes may have been developed. These spatial tunnels linking different star systems might become a reality, and light-speed spacecraft may no longer be confined to science fiction. Once human civilization spans the entire Milky Way, we will have officially entered the realm of a Type 3 civilization according to the Kardashev scale. Karl Kardashev, the Soviet scientist who proposed this scale, originally defined only 3 levels of cosmic civilization. Later, other scientists expanded the system to include levels 4, 5, 6, and even 7 and 8, but these remain ultra-speculative concepts, far beyond what is feasible in the near future. In fact, many scientists believe that Type 2 may already represent the ultimate limit for humanity. Because progressing from Type 2 to Type 3 requires overcoming distances of dozens or even hundreds of light years in a short time, a challenge that is currently completely beyond our technological reach. Although Einstein's theory of relativity predicts the possible existence of wormholes, research shows that natural wormholes could have only formed in the early stages of the Big Bang, when the universe was extremely hot and unstable. As the universe expanded beyond the speed of light and space-time stabilized, such natural wormholes ceased to exist. Without wormholes, traveling across many light years in a short period is nearly impossible. Even if a spacecraft could move at the speed of light, time dilation would cause time aboard the ship and on Earth to pass at different rates, creating an enormous time gap. In other words, such journeys would be one-way trips, unsuitable for civilization expansion. Therefore, the transition from a Type 2 to a Type 3 civilization is the biggest bottleneck humanity may face. And this challenge might not be unique to us. Other intelligent civilizations in the universe may be encountering the same roadblock. This could be a key reason why we have yet to discover extraterrestrial life, because each civilization is trapped within its own home star system, unable to explore or communicate beyond. Ultimately, all civilizations are like fish in isolated ponds, constrained by the speed of light, forever imprisoned within a small corner of space-time. So, how long is 1 light year in kilometers? And why does it make scientists feel so hopeless? Earth's equatorial circumference is approximately 40,000 kilometers. The distance from Earth to the Moon is about 380,000 kilometers. These figures, for some, are still somewhat imaginable, but once we go beyond the entire solar system, kilometers are no longer a useful unit of measure. Astronomers instead use the astronomical unit, AU. 1 astronomical unit equals about 150 million kilometers, the average distance from Earth to the Sun. But beyond the solar system, even astronomical units become too small, so the light year is introduced. For instance, the closest star to us, Proxima Centauri, is 4.22 light-years away. The Milky Way galaxy we live in has a diameter of about 180,000 light-years. With light traveling at 300,000 kilometers per second in 1 year, it covers a distance of about 9.46 trillion kilometers. This number is so huge that the human brain can hardly visualize it, becoming nearly unreal. To help people better understand, let's compare with a concrete example. Imagine a car driving non-stop at 200 kilometers per hour. It would take about 5.4 million years to cover just 1 light year. That's roughly the entire span of human history, from the earliest ancestors to the present day. Currently, the fastest spacecraft ever built by humanity is the Parker Solar Probe, which reaches speeds of approximately 192 kilometers per second. Despite its remarkable velocity, it would still take around 1,500 years to travel just 1 light year. Meanwhile, more familiar spacecraft like Voyager 1 and Voyager 2 travel at about 17 kilometers per second, meaning they would need nearly 18,000 years to cover the same distance. Interestingly, the outermost shell of the solar system, the Oort cloud, has a radius close to 1 light-year. This means that although Voyager 1 and 2 have left the Sun's direct influence, they have not yet completely exited the solar system. They have only crossed beyond the heliosphere, the region influenced by solar wind, and have yet to reach interstellar space. This journey will require tens of thousands more years. We should also remember that the nearest star, Proxima Centauri, is more than 4.22 light-years away from Earth. The nearest galaxy of comparable size to the Milky Way, the Andromeda Galaxy, lies at a much greater distance, about 2.54 million light-years away. And the observable universe spans a staggering diameter of 93 billion light-years, containing at least 2 trillion galaxies, with the average distance between them measured in millions of light-years. With this understanding, we come to realize that even 1 light-year, once thought to be unimaginably vast, is in cosmic terms actually very small. Beyond light-years, there are even larger units such as parsecs and megaparsecs. 1 megaparsec equals approximately 3.26 million light-years. Given current human capabilities, we wouldn't be able to travel even 1/10,000th of that distance in an entire lifetime. You might begin to feel that even light, traveling at a speed of 300,000 kilometers per second, is essentially sluggish and powerless against the vastness of the universe, crawling like a snail. Even a light-speed spacecraft would be ineffective in exploring the cosmos. However, that is only half true. While light may seem slow compared to the universe's vast scale, it is also tied to the phenomenon of time dilation, described by Albert Einstein in his theory of relativity. When an object moves at a speed close to that of light, time within it slows to nearly zero. As a result, if someone were to pilot a spacecraft moving at light speed, they could theoretically reach any destination in the universe instantly, from their own perspective, because time inside the ship would barely pass. It is only those remaining on Earth, within a much slower frame of reference, who would perceive the journey as taking a tremendous length of time. In fact, for photons, the particles of light, time is essentially non-existent from their own perspective. They are emitted and arrive at their destination, whether Earth or the edge of the universe, almost simultaneously. For them, time stands still. It is only us, living on Earth and within a much slower-moving reference frame, who perceive that sunlight takes 8 minutes and 20 seconds to reach Earth, or that light from the Andromeda Galaxy takes 2.54 million years to arrive where we stand. Overall, if humanity truly hopes to travel across this vast universe, overcoming the speed of light barrier is inevitable. Concepts such as warp drives or wormholes are theoretical models that allow faster-than-light travel without violating the known laws of physics. The only problem is, we still don't know how to make them real. Meanwhile, dark energy continues to accelerate the expansion of the universe. According to current estimates, in about 10 trillion years, the universe will stop forming new stars. All remaining matter will slowly be consumed by black holes. Later, even those black holes will evaporate entirely due to Hawking radiation. After tens of millions of trillions of years, the universe will become completely empty and frozen, reaching what is called absolute cold, absolute zero, 0 Kelvin. There will be no light, no matter, no life. The universe will become a frozen hell. This end-of-time scenario is known as the Big Freeze, or heat death. Yet more importantly, this reflects a deeper law of nature, the law of increasing entropy. In simple terms, entropy refers to the level of disorder in a system. The process of increasing entropy is the transition from order to chaos. For example, a room left unattended becomes messy, or a glass falling and shattering into pieces. These are signs of rising entropy. The key point is, this process is naturally irreversible. You can clean the room or glue the glass back together, but it requires external energy. Entropy does not spontaneously decrease. Since the universe is an isolated system, the law of entropy dictates that all ordered structures, like stars, galaxies, even black holes, will gradually break down over time. Stars will fade, galaxies will disperse, and black holes will eventually disappear. Although intelligent civilizations like humanity may create temporary pockets of locally reduced entropy, these are merely fleeting moments. The universe as a whole continues sliding irreversibly toward disorder. However, Nobel Prize-winning physicist Professor Roger Penrose from the UK offers another hypothesis. Perhaps the expansion of the universe, driven by dark matter and dark energy, is only temporary. At some point in the future, gravity may regain dominance, slowing down the expansion. At that point, the universe would cease expanding endlessly and instead begin a slower expansion, eventually halting and reversing into contraction. During this phase, galaxies that once moved away would draw nearer to us. We would observe an increasing number of galaxies in the observable universe. The density of matter would rise until everything merges into one massive black hole, a return to singularity. From that singularity, a new Big Bang might occur, birthing a brand new universe. This is known as the cyclic universe hypothesis. The universe did not originate from nothing, but is instead part of an eternal cycle of expansion and contraction, each time forming a new universe, potentially with completely different physical laws. Perhaps in this current universe, humanity is the only existing civilization. Some scientists believe that the irreversibility of entropy is due to the fact that our universe has only one time axis. This means that time can only flow in one direction, from past to future, and cannot move backward. But if a previous universe or a future one existed with two time axes forming a plane, then past and future would no longer be linear, but would instead be a matter of choice. In such a structure, entropy could be reversed, order could be restored from chaos. This is a bold hypothesis about the possibility of time reversal in alternate universes. Still, one of the defining characteristics of modern physics is that it always leads the times. Today's theories may take hundreds of years to be proven, if ever. In fact, even now, many aspects of Einstein's theory of relativity, first proposed over a century ago, have not been fully confirmed. Phenomena like wormholes or white holes, for instance, have never been observed in reality. Meanwhile, even phenomena already confirmed, such as gravitational waves or time dilation, remain impractical due to current technological limitations. This shows that in physics, it is completely normal for theory to outpace technology by decades or even centuries. Let us look at our observable universe, the part of the cosmos whose light has reached Earth since the Big Bang. The diameter of this observable sphere is approximately 93 billion light-years, and Earth currently lies near the center of this sphere. Because the universe is expanding faster than the speed of light, and because light cannot outrun itself, galaxies farther than 14.6 billion light-years away will never have their light reach Earth. They are forever beyond observation. According to conservative estimates, the observable universe that we can currently detect accounts for only about 1/250th of the total volume of the entire universe. This means the true diameter of the universe must be at least around 23 trillion light-years. If the density of galaxies throughout the universe is similar to that of the observable part, then the total number of galaxies could reach approximately 500 trillion. However, according to data from the Hubble Space Telescope, out of the roughly 2 trillion galaxies in the observable universe, as many as 98% have already lost contact. That is, they are drifting away from us at speeds exceeding the speed of light due to the universe's accelerated expansion. This fact shows that Earth is becoming increasingly isolated in the vastness of space. In theory, if this acceleration continues, eventually all galaxies, except the Milky Way, will drift beyond our observational reach. At that point, the entire observable universe will be reduced to just our galaxy, like a lonely oasis adrift in an infinite ocean of space. Currently, the European Space Agency's Euclid Space Telescope is on a mission to create a detailed 3D map of the universe. In a recent observation, it captured images of over 14 million galaxies. Yet the area of the sky they cover is smaller than the apparent size of the Moon when viewed from Earth, and constitutes less than 1% of the total sky coverage that Euclid aims to map. In the future, astronomers will continue scanning the sky to collect as much data on galaxies as possible in order to build a comprehensive three-dimensional map of the universe. Through this effort, they hope to trace the presence of dark energy and gravitational waves, mysterious forces that govern the structure and ultimate fate of the universe across billions of light years. Unfortunately, because Earth is located within the Milky Way, and the galaxy's zone of obscuration stretches across our night sky, all cosmic maps drawn by humanity, now or in the future, will contain blind spots. These are areas we cannot observe because our own galaxy blocks the view. Only when humans gain the ability to leave the Milky Way will we be able to chart a truly complete map of the entire universe. But ultimately, within the limits of light speed, the best scientists can do is map the observable universe. That is, the part from which light has had time to reach us since the Big Bang. Theoretically, extraterrestrial civilizations could exist beyond this range. If two observable regions of the universe are far enough apart, they won't overlap. In such cases, civilizations within each region would be completely isolated from one another by the speed of light limit and would never become aware of each other's existence. According to Einstein's general theory of relativity, space-time can be warped by mass, and this has been confirmed by many astronomical observations. From this, scientists believe that the universe itself may be curved. More specifically, the actual shape of the universe could be that of a closed space, similar to the surface of a sphere. This implies that if you were to travel in a straight line through space, you would eventually return to your starting point, much like circling the Earth. However, for this to happen, we may need to travel faster than the speed of light, something that remains purely theoretical for now. In conclusion, whether we're discussing the true size or shape of the universe, all of these questions remain open and full of uncertainties. This is because we humans are still a very young civilization, and our understanding of the cosmos is still extremely limited. In the future, as we build more powerful telescopes, the universe will reveal many new wonders that we cannot yet imagine. For example, immediately after the James Webb Space Telescope was launched, it discovered enormous galaxies from the very early universe. These findings forced astronomers to reconsider their understanding, even leading some to propose that the universe might not be 13.8 billion years old, as we previously believed, but possibly as old as 25.6 billion years. From a philosophical standpoint, perhaps the universe created humanity and potentially other civilizations to observe and study itself. If the universe consisted only of inanimate matter, like stars and galaxies, but had no beings to perceive it, then it would be meaningless, because no one would be aware of its existence. But if Earth and humanity are not special in the cosmos, why have we still found no signs of extraterrestrial life? The ultimate answer may lie in the very limit of light speed. Specifically, all intelligent civilizations, including humans, are imprisoned by the speed limit of 300,000 kilometers per second. This traps each civilization within a kind of cosmic fishbowl, just a few dozen light years across, from which they cannot escape to survive or develop further. Just as fish in an aquarium cannot leave the water supply of their tank, humans cannot stray far from nearby stars to expand their civilization across the Milky Way independently. The fishbowl theory is based on the premise that the speed of light cannot be exceeded. If one day humanity were to develop superluminal, faster-than-light technology, then advanced civilizations could rapidly expand throughout the Milky Way, or even the entire universe. But if that were truly possible, we should already have discovered traces of such civilizations left in space. Likewise, they should have discovered us by now. And yet, none of this has happened. The universe remains utterly silent, perhaps suggesting that in our universe, the speed of light truly is an inviolable boundary. Thus, even if alien civilizations exist within the Milky Way or elsewhere in the universe, they are fundamentally isolated, forever confined within their own fishbowls by an unbreakable barrier called the speed of light. Beyond the speed of light limit, Another decisive factor in a civilization's development is cosmic geography. In other words, the natural conditions of the planet and star system where the civilization exists. For example, many super-Earth-type planets have been discovered, which have much greater mass and stronger gravity than Earth. This means that if intelligent life exists on those planets, launching rockets into space would require much larger, more powerful rockets with far more fuel, posing an immense technological challenge. If such a planet has an atmosphere with a high concentration of oxygen, launching a rocket could even trigger catastrophic explosions upon ignition. Alternatively, if a civilization arises within an aging star system on the verge of going supernova, or conversely, within a young, turbulent stellar system still undergoing intense activity, its fate might be sealed from the start. Ferocious stellar storms or lethal radiation bursts from a supernova could completely wipe out that civilization before it even has a chance to develop advanced technologies. In comparison to such harsh conditions, the combination of Earth and our current solar system is truly a rare, peaceful haven. Human civilization was fortunate to emerge during a long, stable phase of our star system. Earth's resources are just sufficient to allow humanity to evolve and begin stepping into space. More importantly, the solar system includes 8 planets and hundreds of natural satellites, offering a rich reservoir of resources to support the development of human civilization. Imagine if the solar system had only Earth. Once we depleted its resources, we would be forced to cross the vast distance of more than 4.22 light-years to reach the nearest star, Proxima Centauri. In that scenario, humanity's resilience in the cosmos would be severely compromised. Therefore, the planet itself and the surrounding cosmic environment play a decisive role in determining the ultimate fate of an intelligent civilization. The Drake equation, a tool used to estimate the number of extraterrestrial civilizations in the Milky Way, suggests there may be dozens of such civilizations. But even if that estimate is correct, with the Milky Way spanning 200,000 light-years and containing over 400 billion stars, the chances of those civilizations ever encountering one another are close to zero. The only signal in history considered to possibly originate from extraterrestrial intelligence is the WOW signal, detected in 1977. However, more recent studies suggest it may have been caused by natural stellar activity, rather than a message from an alien civilization. All these facts suggest one of two possibilities. Either there are no other civilizations beyond Earth, and humanity is the only intelligent life in the universe, or those civilizations are deliberately hiding, silently observing us without revealing their presence. Either way, it means that for a very long time to come, humanity will remain alone in the vast universe. But why does a distance as short as 1 light-year evoke such despair among astronomers? Because within the grand scale of the universe, measuring 93 billion light-years in diameter, the scope of the observable universe, 1 light-year is vanishingly small. Even the closest star to our solar system, Proxima Centauri, lies 4.22 light-years away from Earth. Consider this: the radius of our solar system is nearly 1 light-year, yet even that short distance is currently and likely for centuries unreachable for humanity. The main reason is that our spacecraft today move far too slowly. Whether powered by chemical propulsion or assisted by gravity slingshots, the fastest velocity we've achieved is about 200 kilometers per second, less than 1/1000th the speed of light. Without gravity assist maneuvers, the sustained cruising speed of modern spacecraft is only about 1/10,000th the speed of light, or approximately 30 kilometers per second. This means that to travel just 1 light-year, a probe would need to fly continuously for 10,000 years. To take a specific example, Voyager 1 and Voyager 2, launched in 1977, travel at about 17 kilometers per second. Based on their declining energy levels, astronomers estimate it will take another 30,000 years before they officially cross the boundary of the solar system. Meanwhile, light in space moves at 300,000 kilometers per second. If it travels non-stop for 1 year at that speed, it covers the distance of 1 light year, about 9.46 trillion kilometers. Because light is the maximum speed in the universe, when we observe galaxies millions of light years away, we're actually seeing their past images, the light they emitted millions of years ago. The photons forming their current image are still en route to Earth and won't reach our telescopes for millions of years. Interestingly, above the light year lies a larger unit called the parsec, with 1 parsec approximately equal to 3.26 light years. The highest commonly used unit is the megaparsec, equivalent to 1 million parsecs, or 3.26 million light years. If 1 light year is 9.46 trillion kilometers, then a car traveling at 100 kilometers per hour would need 10.8 million years to cover that distance. And if you want to imagine how far a megaparsec is, just multiply that number by 3.26 million. Clearly, cosmic distances have far surpassed the limits of human imagination. There are no reference objects, no comparative units, only astronomical numbers that border on the surreal. Even under the most optimistic assumptions, if controlled nuclear fusion were applied to spacecraft and combined with pulse propulsion or radiation drive, a standard fusion-powered ship might reach 1% of the speed of light, about 3,000 kilometers per second. At that speed, it would take just minutes to reach the moon. As long as we remain within the solar system, that speed would be more than sufficient for exploration missions. However, to noticeably trigger time dilation, the relativistic effect where time slows as speed increases, a spacecraft would need to reach 1/10 to 1/5 the speed of light, or about 30,000 to 60,000 kilometers per second. At that velocity, it would only take seconds to reach the moon, and time on board would pass significantly slower than on Earth. If a ship could sustain such extreme speed for extended periods, its passengers might effectively travel to the future. For example, while 10 years might pass on the ship, 12 years could pass on Earth. This is the very phenomenon of time dilation described by Einstein in special relativity, and it's one theoretical method of time travel to the future. As for building a spacecraft that can reach light speed, technologies like warp drives and wormholes remain far beyond the scope of modern physics. Perhaps centuries from now, when scientists uncover the limits of relativity and build a new theoretical framework, similar to how Einstein replaced Newtonian mechanics with modern physics, then the dream of light-speed travel might finally become reality. Looking back in time, the only suspected signal ever received by humans from an extraterrestrial civilization was the WOW signal detected in 1977 by the Big Ear radio telescope. It was a narrowband radio signal that originated from beyond the solar system but still within the Milky Way, estimated at a distance of around 200 light years. The signal lasted just 72 seconds before vanishing completely. In the decades since, it has never reappeared. When recorded, it was encoded using a symbolic system combining letters and numbers. The area where the WOW signal was detected is known for being extremely quiet, with very little radio activity. When the signal abruptly intensified, its strength was encoded using characters from 1 to 9 and then A to Z. Specifically, the sequence 6EJ5 indicated a sharp, unusual spike, almost like someone had sent a burst of Morse code-like pulses, peaking and then fading. This was an extremely rare narrowband signal and matched the kind of transmission humanity would expect from an intelligent extraterrestrial source. It was so striking that astronomer Jerry R. Ehman, who first detected it, scribbled WOW next to the printed data, giving the signal its legendary name, the WOW signal. Unfortunately, at that time, the Big Ear radio telescope was fixed in place and could only scan the sky by relying on Earth's rotation. This meant it couldn't keep its focus on the target long enough to continue observing the signal. As a result, astronomers missed the chance to record the full WOW signal. Moreover, the technology of that era wasn't advanced enough to determine exactly which star system the signal originated from. Consequently, WOW quickly became a fleeting phenomenon, one that caused a stir, then faded into silence. In the decades that followed, radio telescopes around the world repeatedly aimed at the same region of the sky to try to detect the signal again, but aside from some minor background noise, nothing significant was found. Some scientists suggest that the WOW signal might have originated from a very distant region of the universe. We were only able to hear it thanks to the gravitational lensing effect, where light or radio waves are bent and amplified by the strong gravity of an intervening massive object. Other hypotheses claim the signal might have come from a passing comet, or perhaps from a distant spacecraft. Some even speculate that it was the result of radio wave reflections from artificial satellite debris. But since the WOW signal has never repeated, none of these theories can be confirmed. In a science fiction film, a similar signal to the WOW was said to come from the star Vega. According to the plot, extraterrestrials had received Earth's television broadcasts from decades ago and responded by sending a signal back to Earth. Today, the most promising facility in the search for extraterrestrial signals is China's Fast Radio Telescope, often referred to as the Sky Eye. It is the world's largest single-dish radio telescope, and one of its main missions is to listen for unusual signals from the distant cosmos. Although the brilliant physicist Stephen Hawking repeatedly warned humanity against actively sending messages into the universe so as not to wake up potentially dangerous civilizations, and Liu Cixin's dark forest theory echoes this caution, telescopes like FAST only listen and do not transmit. Therefore, they are considered safe and pose no risk of revealing Earth's location. In fact, the famous Arecibo message humanity sent into space decades ago, a powerful radio signal broadcast into the cosmos, has only reached a region just a few dozen light-years from Earth. The number of star systems it has touched can be counted on one hand, and the chances of life existing within them are extremely low. Furthermore, the signal's transmission power wasn't very strong, and it may have been distorted, scrambled, or entirely buried in cosmic noise. Nevertheless, whatever is or will happen, the possibility of extraterrestrial civilizations remains the greatest unknown in the history of human civilization. There is no second candidate as significant. They may never be detected by us. Or perhaps, in the very next moment, they could pilot a light-speed ship and suddenly appear in Earth's orbit. And why do we say that? If humans are the only intelligent beings in the universe, that is truly a terrifying thought. Imagine a fish living in a tank of pristine water. Throughout its life, it never encounters another fish like itself. In the end, it may believe that it is the only creature of its kind in the entire world. Only the observer outside, the human, knows that the fish is merely swimming in a small tank. Human civilization's place in the universe today is not so different from that lonely fish. In the observable universe of over 2 trillion galaxies, astronomers have yet to find any evidence of an extraterrestrial civilization. Although humans have discovered more than 5,000 exoplanets, some of which are labeled super-Earths or Earth 2.0, no signs of life have been detected on any of them so far. At least for now, it seems there's only one civilization in the entire universe: humanity on Earth. Earth appears to be the only planet with life. But our rational mind tells us this is almost impossible. Solar system-like structures and Earth-like planets are not rare among the millions upon millions of stellar systems in the cosmos. Even if the odds of an alien civilization arising were only 1 in 100 million, then in the current universe, the number of alien civilizations should far exceed Earth's population. That is why many scientists, including Elon Musk, believe humanity is merely a fish in the bowl. That bowl could be the solar system, or perhaps a part of the Milky Way. After all, if Voyager 1 and 2 still need 30,000 more years to exit the solar system, then exploring the entire Milky Way remains purely science fiction at this point. Thus, although the fish in the bowl theory cannot yet be proven, we've seen similar scenarios on Earth. Nature reserves and protected habitats for uncontacted tribes show that advanced civilizations tend to observe and protect lower civilizations without interfering directly. This leads to a thought-provoking possibility. Humanity may be isolated and silently observed by a more advanced civilization. The evidence? Precisely the fact that we haven't found any extraterrestrial civilizations despite decades of effort. Perhaps once we escape the solar system or the Milky Way, we'll immediately realize we are not alone in the universe. The only way to break this isolation is by developing spacecraft that can approach the speed of light, using technologies like controlled nuclear fusion or warp drives. However, these technologies are still far beyond our reach today. Currently, the most promising technology to bring spacecraft closer to light speed is light sail propulsion. Theoretically, if the sail is large and light enough, it can continuously accelerate under the pressure of sunlight. After a few decades, it could reach 20% of the speed of light, or about 60,000 kilometers per second. Moreover, every time it passes by a star, the light sail could receive another speed boost. If the flight path is carefully calculated, then within a few centuries, a light sail probe could realistically achieve near light speed travel. Unfortunately, we still cannot be sure whether extraterrestrial civilizations will be good or bad. There's no evidence suggesting that a more advanced civilization must also be more morally upright. For this reason, the genius physicist Stephen Hawking, in the final years of his life, repeatedly warned humanity not to actively contact aliens. Lou Chisholm, with his famous dark forest hypothesis from the Three Bodies series, expressed the same concern. The universe is a forest filled with predators, where those who make a sound first will be the first to be eliminated. Regardless of the truth, at the very least, we know that humanity exists. We may be the only civilization or the most advanced one in the entire universe. If this is true, then all the resources of the universe are available for us to explore, provided we are capable of reaching the era of great space development. On October 15, 1997, the Cassini-Huygens probe was launched into space. After 4 years traveling through the solar system, the spacecraft entered Saturn's orbit, beginning a 20-year journey to explore this giant planet. Out of concern that the spacecraft might later lose control and crash into one of Saturn's moons, scientists made a plan. To avoid accidental collisions that could contaminate environments and affect the potential for life on Saturn's moons, in 2017, mission engineers decided to proactively alter Cassini's orbit, steering it straight into Saturn's atmosphere, ending the mission in a controlled way. During this suicide dive, Cassini wasn't shut down, but continued capturing images and gathering data until the final moments. Thanks to this, we were able to witness unprecedented images of Saturn's atmosphere. In the early stages of its descent, Cassini made several passes over Saturn's North Pole and flew deep into the F-ring, a narrow and complex part of the ring system. There, it observed the mysterious hexagonal storm and the northern region illuminated by sunlight. Additionally, the spacecraft conducted more detailed observations of Enceladus, a moon known for its geyser-like plumes similar to Earth's. Cassini confirmed that beneath Enceladus's thick ice crust lies a liquid ocean, where extraterrestrial life could be emerging. On April 22, 2017, Cassini performed its final flyby of Titan before redirecting itself into the gap between Saturn and its inner rings, a region never before traversed by any spacecraft. Cassini skimmed above Saturn's cloud tops at an altitude of about 3,100 kilometers, and for the first time, scientists observed ring material falling onto the planet at a rate of 10 tons per second, mainly water ice. The total water content in Saturn's rings is greater than all the water on Earth. Cassini also discovered that Saturn's magnetic field aligns almost perfectly with its rotational axis, something not seen on any other planet in the solar system. Even more importantly, the probe helped precisely determine Saturn's rotation period, 10 hours, 33 minutes, and 38 seconds. Until it was torn apart by Saturn's gravity, Cassini maintained antenna operations and transmitted data back to Earth, including its final image of Saturn, a deeply emotional end to a remarkable 20-year mission. Currently, NASA has launched the Europa Clipper mission targeting Jupiter's moon Europa. Its main objective is to study the ancient ice layers in the deep subsurface ocean, one of the most promising places for potential life in the solar system. This shows that, while Earth may be the only known inhabited planet, the moons of Jupiter and Saturn still hold strong astrobiological potential. In the future, after completing the exploration of the Moon and Mars, humanity's next step may be to develop hundreds of natural satellites orbiting Jupiter and Saturn, marking a major step toward becoming an interplanetary civilization. However, the greatest barrier to space exploration today is speed. Whether probe or crewed missions, current speeds only reach a few dozen kilometers per second, less than 1% of the speed of light, 3,000 kilometers per second. At this pace, a trip to Mars takes at least 6 months, and journeys to Jupiter or Saturn take years. Only when controlled nuclear fusion, a technology often said to be just 50 years away, becomes a reality, can space travel speeds make a leap. At that point, spacecraft could reach 1 to 10% of light speed, 3,000 to 30,000 kilometers per second, enabling flexible travel throughout the solar system. Then, the solar system would truly become a resource exploitation zone for human civilization, and we would officially enter the interplanetary or even interstellar era. However, if CO2 emissions continue to rise, the timing of Earth's next ice age may be delayed. In Earth's history, the first ice age occurred about 2.5 billion years ago, triggered by the explosive growth of cyanobacteria, which increased atmospheric oxygen and reduced global greenhouse gases, leading to the Huronian glaciation. For 300 million years, Earth was almost entirely frozen. Ice sheets stretched from the poles to the equator. Though Earth eventually thawed and returned to a temperate state, glacial periods continued in cycles. For example, the Cryogenian glaciation occurred between 720 and 635 million years ago, with many smaller ice ages following. The most recent ice age ended about 20,000 years ago, during which ice covered all of Poland, Germany, most of France, and extended to the Alps. Its end paved the way for human civilization to emerge roughly 10,000 years ago. According to scientific studies, this ice age may have ended due to Antarctica's separation from Australia and South America. The formation of the Drake Passage between Antarctica and South America created a cold ocean current circling the continent, greatly influencing global climate. If global warming accelerates rapidly in the future, Earth's average temperature may rise to levels that melt both polar ice caps. In that case, sea levels would rise quickly, inundating coastal regions. Because most of humanity's industrial, economic, and technological centers are near the sea, the consequences would be hard to quantify. However, given today's scientific and technological development, the scenario of a runaway greenhouse effect seems unlikely. This is because, in a few hundred years, humanity may master controlled nuclear fusion, a clean, safe, and nearly limitless energy source. This would completely replace fossil fuels and usher us into the era of a Type 1 civilization, officially launching the age of cosmic conquest. By then, all heavy industries will have been relocated to space, and metal resources will be extracted from asteroids instead of Earth. This transition will significantly reduce the human footprint on our blue planet. Within a few centuries, Earth may return to a state resembling the pre-industrial era, like a vast garden floating in the universe. In fact, what scientists are currently more concerned about is not climate change, but rather the alteration of Earth's magnetic field. Throughout history, Earth's magnetic field has flipped multiple times, a phenomenon where the North and South poles switch places. If this happens again, it could cripple the entire global navigation system. Furthermore, if Earth's core gradually cools, the magnetic field could weaken significantly. In such a case, Earth could very well become a second Mars, cold, depleted of atmosphere, and no longer able to shield life. In summary, Earth is not an ideal planet for humanity to live on forever. One day, it may no longer be suitable. What we must do is use the time we have left to expand life into space, at least within the bounds of the solar system. to become a multiplanetary species. Astronomers are also researching the cosmic microwave background, CMB radiation, a kind of light fingerprint left over from the birth of the universe. Because the universe is constantly expanding at an accelerated pace, those signals take on shapes that resemble wisps of feathers. Remarkably, in the direction of the Cygnus constellation, about 1,800 light-years away from Earth, scientists have discovered a super-Earth named Kepler 452b. This planet is 5 times heavier than Earth, with a radius about 1.5 times larger. Most importantly, it lies within the habitable zone of its star, much like Earth's position in the solar system. According to astronomical calculations, Kepler 452b has an Earth similarity index of up to 85%. Barring the stronger gravitational force, it is nearly Earth's twin brother. It is considered the most suitable candidate for future human migration and also holds the highest potential for harboring life or even an extraterrestrial civilization. In astronomical units, AU, Kepler 452b orbits its star at a distance of 1.04 AU, slightly farther than the Earth-Sun distance. As a result, the gravitational force it receives from its star is slightly weaker, and it takes 385 days to complete one orbit, making a year on this planet longer than a year on Earth. Not the best news for workers waiting for their vacation. One surprising fact is that Kepler 452b is about 6 billion years old, approximately 1.5 billion years older than Earth. This means that if life ever emerged there, it could have undergone evolution millions of years ahead of Earth. Theoretically, if there were an alien civilization on this planet, they might have developed technology far more advanced than ours, by millions of years. However, reality seems to suggest otherwise. Since Kepler 452b is only 1,800 light-years away, what we're seeing now is its image from 1,800 years ago. No suspicious radio signals have been detected, and there are no unusual atmospheric changes such as industrial CO2 spikes. All current evidence points to the absence of an advanced civilization. Perhaps only simple life forms exist there, or at best, a primitive Stone Age-like civilization. With a gravity 2.2 times stronger than Earth's, the planet's mountain ranges would be lower, and its flora and fauna would tend to be short and stocky. Moreover, launching rockets off the planet would be extremely difficult, possibly creating a natural barrier to the rise of a high-tech civilization, a sort of cosmic, geographical destiny. In the future, if humanity reaches Kepler 452b, we might encounter a scenario reminiscent of the movie Avatar, a planet with small-bodied, low-tech inhabitants living in harmony with nature. The question is, will humans choose to be Columbuses discovering new lands, or will we be repelled by united natives as in Avatar? Only the future can answer that. As for our capabilities, humanity currently ranks at 0.7 on the Kardashev scale, still centuries away from a Type 1 civilization, one that can harness all of a planet's energy. Reaching a Type 2 civilization, capable of building a Dyson sphere to capture all the energy of a star, may take tens of thousands of years. Along this evolutionary path, humanity could be wiped out by numerous existential threats: the rise of AI, asteroid impacts, supernova explosions, nuclear war. All of these are considered great filters, existential bottlenecks in the development of any civilization. To avoid such catastrophe, astronomers are intensifying their search for habitable planets to help humans spread life beyond Earth, so we don't put all our eggs in one basket. This is also why Elon Musk consistently advocates for Mars colonization, to make humans a multiplanetary species. Why can't time be reversed? In physics, time is the most unique phenomenon. It has only one direction, always moves forward, and cannot go backward. That's why we can remember the past, but cannot remember the future. Physicist Albert Einstein once said, "Time is an illusion created by the human brain to better comprehend the universe." According to him, it's a cognitive tool shaped by evolution. To date, the shortest unit of time defined in theoretical physics is Planck time, the time it takes for a photon, a particle of light, to travel one Planck length. This interval is unimaginably short, about 10 memorspore seconds, a scale at which all known physical laws break down. However, this is purely a theoretical construct with little practical meaning. In everyday life, once a single minute has passed, no effort can bring it back. Even if we could force every particle in the universe to return to the exact state of 1 minute ago, doing so would take time, making the process not a rewind, but a reconstruction. Thus, time's irreversibility appears to be a fundamental law of the universe, just like how the speed of light cannot be surpassed. But Einstein didn't fully agree. In his general theory of relativity, time, like space, can be warped by speed or mass. Specifically, the faster an object moves, the slower time passes. At the speed of light, time halts completely. Similarly, near an extremely strong gravitational source like a black hole, time slows down. To an outside observer, it nearly stands still. In fact, merely being near a black hole is enough to stretch time so that 1 hour there equals 7 years on Earth, a form of one-way time travel into the future, entirely possible if we can harness speed and gravity. However, Einstein provided no solution for traveling into the past. Many speculate that if one reaches the speed of light, time stops, and if surpassed, time would reverse. But in this universe, nothing can exceed the speed of light. The only glimmer of hope for traveling back in time may lie in the theoretical technology of space-time tunnels, also known as wormholes. For example, if time and space are truly unified, then a wormhole doesn't just connect 2 points in space, such as between Earth and Mars, but also links the moments in time at each end. This means that if you travel through a wormhole to Mars today, your destination might be yesterday or tomorrow on Mars. The randomness of time within a wormhole introduces the possibility of traveling backward in time. However, this gives rise to a major problem: the paradoxes of time travel. Suppose you return to the past and meet your favorite musician before he has composed any of his works. You play him a piece of music that he will eventually write in the future. He's inspired and begins composing that exact piece. The result: the music seemingly comes from nowhere. It exists only because you brought it from the future to the past and then back again. It has no original source, becoming a causeless artifact in history. Some physicists argue that a time traveler cannot truly alter the past because time is inherently self-consistent. That is, any changes made will be subtly corrected so that the timeline remains on its original, main path. The time traveler may believe they are changing the past, but in reality, they are merely fulfilling a role they always had in shaping the present. However, if the multiverse hypothesis, parallel universe, is true, then time travel simply becomes a transfer from one timeline to another. In that case, you can freely change history, because each universe has its own separate timeline that doesn't overlap with the others. There would be no mechanism enforcing temporal consistency, because you're no longer in your original universe. You could create a new world, entirely different from the one you knew, and you would become part of the force, rewriting the history of that universe. In 2011, a group of teachers and students at a high school in the United States folded a roll of toilet paper 13 times, reaching a world record for the number of folds. However, under normal conditions, a sheet of paper can typically only be folded 6 to 8 times due to limitations in thickness and resistance. Take a standard A4 sheet of paper, which is just 0.104 millimeters thick. With each fold doubling its thickness, the size increases exponentially. After 14 folds, that same sheet would reach a height of 1.64 meters, nearly the height of an adult. This is where the terrifying power of exponential growth begins to reveal itself. After 23 folds, the paper's height would reach 838.36 meters, taller than the Burj Khalifa, the world's tallest building. At 27 folds, it would stand 13,000 meters tall, surpassing Mount Everest. By the 28th fold, it would be 26,000 meters high, officially entering the edge of space. By the 36th fold, it would stretch 6,871 kilometers, about half the diameter of Earth. At the 42nd fold, the paper would span 440,000 kilometers, enough to bridge Earth and the Moon. From there, each fold increases the length by distances measured in light years. By the 49th fold, it reaches Mars, about 55 million kilometers away. At 51 folds, it reaches the Sun at 150 million kilometers. At 56 folds, it surpasses Pluto's orbit, reaching 7.2 billion kilometers. At 58 folds, the paper catches up to Voyager 1, the farthest man-made object in space. By the 68th fold, it exits the solar system entirely, entering interstellar space with a length equivalent to 2 light years. From the 69th fold onward, each new fold spans astronomical distances. The 69th fold connects the Sun to Proxima Centauri, the nearest star at 4.22 light-years away. The 81st fold takes it to the center of the Milky Way. The 84th fold stretches across the full width of our galaxy, 200,000 light-years. The 90th fold spans 13 million light-years, beyond our local group of galaxies. And if you continue folding to the 103rd time, the paper would stretch over 107 billion light-years, longer than the 93 billion light-year diameter of the observable universe. Of course, the actual universe could be far larger, as it is continuously expanding at speeds exceeding that of light. In fact, the creation of new space-time could be happening even faster than the pace of exponential folding. Some theories suggest that the universe might be finite, but unbounded, like a giant circle. Once the paper is folded enough times, it could begin to curve with the geometry of space-time and eventually loop back to its origin, forming a closed loop. All these numbers and vivid images serve to emphasize one thing: exponential growth is one of the most astonishing and unpredictable phenomena in the universe. From a thin sheet of paper, if folded enough times, it could theoretically envelop the cosmos. And in reality, the development of human civilization seems to be following a similar exponential trend. In just the past year, humanity's energy consumption has vastly exceeded the total used across thousands of years in history. As we enter the space age and master controlled fusion technology, we may evolve into a Type 1 civilization, one that harnesses all the energy on its planet. But if we aim to become a Type 2 civilization capable of constructing a Dyson sphere, a colossal structure that surrounds a star to absorb all its energy, we would need to dismantle a planet the size of Jupiter. For this reason, many astronomers believe the solar system is not an ideal environment for building such a structure. Nonetheless, regardless of which level we aim for, one thing is certain: if humanity's exponential growth continues, a magnificent future lies ahead, one filled with both awe-inspiring possibilities and profound challenges.